Section 25 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Calculus Made Easy by Silvanus P. Thompson. Section 25. Exercises 11. Split into fractions. 1. 3x add 5 all over, open brackets, x minus 3, close brackets, open brackets, x add 4, close brackets. Answer. 2 over x minus 3 add 1 over x add 4. 2. 3x minus 4 all over, open brackets, x minus 1, close brackets, open brackets, x minus 2, close brackets. Answer. 1 over x minus 1 add 2 over x minus 2. 3. 3x add 5 all over x squared add x minus 12. Answer. 2 over x minus 3 add 1 over x add 4. 4. X add 1 all over x squared minus 7x add 12. Answer. 5 over x minus 4 minus 4 over x minus 3. 5. X minus 8 all over, open brackets, 2x add 3, close brackets, open brackets, 3x minus 2, close brackets. Answer. 19 over 13, open brackets, 2x add 3, close brackets, minus 22 over 13, open brackets, 3x minus 2, close brackets. 6. X squared minus 13x add 26, all over, open brackets, x minus 2, close brackets, open brackets, x minus 3, close brackets, open brackets, x minus 4, close brackets. Answer. 2 over x minus 2, add 4 over x minus 3, minus 5 over x minus 4. 7. X squared minus 3x add 1, all over, open brackets, x minus 1, close brackets, open brackets, x add 2, close brackets, open brackets, x minus 3, close brackets. Answer. 1 over 6, open brackets, x minus 1, close brackets, add 11 over 15, open brackets, x add 2, close brackets, add 1 over 10, open brackets, x minus 3, close brackets. 8. 5x squared add 7x add 1, all over, open brackets, 2x add 1, close brackets, open brackets, 3x minus 2, close brackets, open brackets, 3x add 1, close brackets. Answer. 7 over 9, open brackets, 3x add 1, close brackets, add 71 over 63, open brackets, 3x minus 2, close brackets, minus 5 over 7, open brackets, 2x add 1, close brackets. 9. X squared over x cubed minus 1. Answer. 1 over 3, open brackets, x minus 1, close brackets, add 2x add 1, all over 3, open brackets, x squared add x add 1, close brackets. 10. X to the power 4 add 1, all over x cubed add 1. Answer. X add 2 over 3, open brackets, x add 1, close brackets, add 1 minus 2x, all over 3, open brackets, x squared minus x add 1, close brackets. 11. 5x squared add 6x add 4, all over, open brackets, x add 1, close brackets, open brackets, x squared add x add 1, close brackets. Answer. 3 over x add 1 add 2x add 1, all over, x squared add x add 1. 12. X over, open brackets, x minus 1, close brackets, open brackets, x minus 2 close brackets squared. Answer 1 over x minus 1 minus 1 over x minus 2 add 2 over open brackets x minus 2 close brackets squared. 13. X over open brackets x squared minus 1 close brackets open brackets x add 1 close brackets. Answer 1 over 4 open brackets x minus 1 close brackets minus 1 over 4 open brackets x add 1 close brackets add 1 over 2 open brackets x add 1 close brackets squared. 14. X add 3 all over open brackets x add 2 close brackets squared open brackets x minus 1 close brackets. Answer 4 over 9 open brackets x minus 1 close brackets minus 4 over 9 open brackets x add 2 close brackets minus 1 over 3 open brackets x add 2 close brackets squared. 15. 3x squared add 2x add 1 all over open brackets x add 2 close brackets open brackets x squared add x add 1 close brackets squared. Answer 1 over x add 2 minus x minus 1 all over x squared add x add 1 minus 1 over open brackets x squared add x add 1 close brackets squared. 16. 5x squared add 8x minus 12 all over open brackets x add 4 close brackets cubed. Answer 5 over x add 4 minus 32 over open brackets x add 4 close brackets squared add 36 over open brackets x add 4 close brackets cubed. 17. 7x squared add 9x minus 1 all over open brackets 3x minus 2 close brackets to the power 4. Answer 7 over 9 open brackets 3x minus 2 close brackets squared add 55 over 9 open brackets 3x minus 2 close brackets cubed add 73 over 9 open brackets 3x minus 2 close brackets to the power 4. 18. X squared over open brackets x cubed minus 8 close brackets open brackets x minus 2 close brackets. Answer 1 over 6 open brackets x minus 2 close brackets add 1 over 3 open brackets x minus 2 close brackets squared minus x over 6 open brackets x squared plus 2x plus 4 close brackets. End of section 25. Section 26 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Calculus Made Easy by Silvanus P. Thompson. Chapter 13. Other Useful Dodges, Part 2. Differential of an inverse function. Consider the function y equals 3x. It can be expressed in the form x equals y over 3. This latter form is called the inverse function to the one originally given. If y equals 3x, dy over dx equals 3. If x equals y over 3, dx over dy equals 1/3. And we see that dy over dx equals 1 over dx over dy, or dy over dx times dx over dy equals 1. Consider y equals 4x squared. Dy over dx equals 8x. The inverse function is x equals y to the power half over 2, and dx over dy equals 1 over 4 square root y equals 1 over 4 times 2x equals 1 over 8x. Here again, dy over dx times dx over dy equals 1. It can be shown that for all functions which can be put into the inverse form, one can always write dy over dx times dx over dy equals 1, or dy over dx equals 1 over dx over dy. It follows that, being given a function, if it be easier to differentiate the inverse function, this may be done, and the reciprocal of the differential coefficient of the inverse function gives the differential coefficient of the given function itself. As an example, suppose that we wish to differentiate y equals the square root of 3 over x minus 1. We have seen one way of doing this, by writing u equals 3 over x minus 1 and finding dy over du and du over dx. This gives dy over dx equals minus 3 over 2x squared square root of 3 over x minus 1. If we had forgotten how to proceed by this method, or wished to check our result by some other way of obtaining the differential coefficient, or for any other reason we could not use the ordinary method, we can proceed as follows. The inverse function is 3 over 1 add y squared. Dx over dy equals minus 3 times 2y over open brackets 1 add y squared close brackets squared equals minus 6y over open brackets 1 add y squared close brackets squared. Hence dy over dx equals 1 over dx over dy equals minus open brackets 1 add y squared close brackets squared over 6y equals minus open brackets 1 add 3 over x minus 1 close brackets squared all over 6 times square root of 3 over x minus 1 equals minus 3 over 2x squared square root 3 over x minus 1. Let us take as another example y equals 1 over cube root of theta add 5. The inverse function is theta equals 1 over y cubed minus 5, or theta equals y to the power of minus 3 minus 5, and d theta over dy equals minus 3y to the power of minus 4 equals minus 3 cube root of open brackets theta add 5 close brackets to the power 4. It follows that dy over d theta equals minus 1 over 3 times the square root of open brackets theta add 5 close brackets to the power 4, as might have been found otherwise. We shall find this dodge most useful later on. Meanwhile, you are advised to become familiar with it by verifying by its means the results obtained in exercises 1, page 24, numbers 5, 6, 7, examples, page 67, numbers 1, 2, 4, and exercises 6, page 72, numbers 1, 2, 3, and 4. You will surely realise from this chapter and the preceding that in many respects the calculus is an art rather than a science, an art only to be acquired, as all other arts are, by practice. Hence you should work many examples, and set yourself other examples, to see if you can work them out, until the various artifices become familiar by use. End of section 26.
Section 27 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Reading by Paul King, pjk.scripts.mit.edu/pkj. Calculus Made Easy by Silvanus P. Thompson. Chapter 14. On the True Compound Interest and the Law of Organic Growth, Part 1a. Let there be a quantity growing in such a way that the increment of its growth during a given time shall always be proportional to its own magnitude. This resembles the process of reckoning interest on money at some fixed rate, for the bigger the capital, the bigger the amount of interest on it in a given time. Now we must distinguish clearly between two cases in our calculation, according as the calculation is made by what the arithmetic books call simple interest, or by what they call compound interest. For in the former case the capital remains fixed, while in the latter the interest is added to the capital, which therefore increases by successive additions. 1. At simple interest. Consider a concrete case. Let the capital at start be £100, and then the rate of interest be 10% per annum. Then the increment to the owner of the capital will be £10 every year. Let him go on drawing his interest every year and hoard it by putting it by in a stocking or locking it up in his safe. Then if he goes on for 10 years, by the end of that time he will have received 10 increments of £10 each, or £100, making, with the original 100, a total of £200 in all. His property would have doubled itself in 10 years. If the rate of interest had been 5%, he would have had to hoard it for 20 years to double his property. If it had been only 2%, he would have had to hoard it for 50 years. It is easy to see that if the value of the yearly interest is 1 over n of the capital, he must go on hoarding for n years in order to double his property. Or if y be the original capital and the yearly interest is y over n, then at the end of n years his property will be y plus n times y over n equals 2y. 2. At compound interest. As before, let the owner begin with a capital of £100, earning interest at the rate of 10% per annum, but instead of hoarding the interest, let it be added to the capital each year so that the capital grows year by year. Then at the end of 1 year the capital will have grown to £110. And in the second year, still at 10%, this will earn £11 interest. He will start the third year with £121, and the interest on that will be £12 2 shillings, so that he starts the fourth year with £133 2 shillings, and so on. It is easy to work it out, and to find that at the end of the 10 years the total capital would have grown to £259 7 shillings 6 pence. In fact, we see that at the end of each year, each pound would have earned 1/10 of a pound, and therefore, if this is always added on, each year multiplies the capital by 11 over 10, and if continued for 10 years, which will multiply by this factor 10 times over, we will multiply the original capital by 2.59374. Let us put this in the symbols. Put y0 for the original capital, 1 over n for the fraction added on at each of the n operations, and y sub n for the value of the capital at the end of the nth operation. Then y sub n equals y0 multiplied by open bracket 1 plus 1 over n close bracket raised to the power n. But this mode of reckoning compound interest once a year is really not quite fair, for even during the first year the £100 ought to have been growing. At the end of half a year it ought to have been at least £105, and certainly it would have been fairer had the interest for the second half of the year been calculated on £105. This would be equivalent to calling it 5% per half year with 20 operations, therefore at each of which the capital is multiplied by 21 over 20. If reckoned this way, by the end of 10 years the capital would have grown to £265 6 shillings 7 pence for open bracket 1 plus 1 over 20 close bracket to the power 20 equals 2.653. But even so, this process is still not quite fair, for by the end of the first month there will be some interest earned, and a half yearly reckoning assumes that the capital remains stationary for 6 months at a time. Suppose we divided the year into 10 parts and reckon a 1% interest for each tenth of the year. We now have 100 operations lasting over 10 years, or y sub n equals £100 multiplied by open bracket 1 plus 1 over 100 close bracket to the power 100, which works out to £270 9 shillings 7.5 pence. Even this is not final. Let the 10 years be divided into 1,000 periods, each of 1/100th of a year, the interest being 1 over 10% for each period. Then y sub n equals 100 pounds multiplied by open bracket 1 plus 1 over 1000 close bracket raised to the power of 1000, which works out to 271 pounds 13 shillings 10 pence. Go even more minutely and divide the 10 years into 10,000 parts, each of 1/1000th of a year, with interest at 1/100th of 1%. Then y sub n equals 100 pounds multiplied by open bracket 1 plus 1 over 10,000 close bracket to the power of 10,000, which amounts to 271 pounds 16 shillings and 3.5 pence. Finally, it will be seen that what we are trying to find in reality is the ultimate value of the expression 1 plus 1 over n raised to the power n, which, as we see, is greater than 2, and which, as we take n larger and larger, grows closer and closer to a particular limiting value. However big you make n, the value of this expression grows nearer and nearer to the figure 2.71828 and so on, a number never to be forgotten. Let us take geometrical illustrations of these things. In figure 36, OP stands for the original value. OT is the whole time during which the value is growing. It is divided into 10 periods, in each of which there is an equal step up. Here dy by dx is a constant, and if each step up is 1/10 of the original OP, then by 10 such steps the height is doubled. If we had taken 20 steps, each of half the height shown, at the end the height would still be just doubled, or n such steps, each of 1 over n, the original height OP, would suffice to double the height. This is the case of simple interest. Here is one growing until it becomes 2. In figure 37, we have the corresponding illustration of the geometrical progression. Each of the successive ordinates is to be 1 plus 1 over n, that is, n plus 1 over n times as high as its predecessor. The steps up are not equal, because each step up is now 1 over n of the ordinate of that part of the curve. If we had literally 10 steps with 1 plus 1 over 10 for the multiplying factor, the final total would be open bracket 1 plus 1 over 10 close bracket to the power 10, or 2.594 times the original 1. But if we only take n sufficiently large and the corresponding 1 over n sufficiently small, then the final value open bracket 1 plus 1 over n close bracket raised to the power n, to which unity will grow to be 2.71828. Epsilon. To this mysterious number 2.7182818, etc., the mathematicians have assigned as a symbol the Greek letter epsilon. All schoolboys know that the Greek letter pi stands for 3.141592, etc., but how many of them know that epsilon means 2.71828? Yet it is an even more important number than pi. What then is epsilon? Suppose we were to let 1 grow at simple interest till it became 2. Then, if at the same nominal rate of interest and for the same time we were to let 1 grow at a true compound interest instead of simple, it would grow to the value epsilon. This process of growing proportionately at every instant to the magnitude of that instant some people call a logarithmic rate of growing. Unit logarithmic rate of growth is that rate which in unit time will cause 1 to grow to 2.718281. It might also be called the organic rate of growing, because it is characteristic of organic growth, in certain circumstances, that the increment of the organism in a given time is proportional to the magnitude of the organism itself. If we take 100% as the unit of rate, and any fixed period as the unit of time, then the result of letting 1 grow arithmetically at unit rate for unit time will be 2, while the result of letting one grow logarithmically at unit rate for the same time will be 2.71828, and so on. A little more about epsilon. We have seen that we require to know what value is reached by the expression open bracket 1 plus 1 over n close bracket to the power n, where n becomes indefinitely great. Arithmetically, here are tabulated a lot of values which anyone can calculate out by the help of an ordinary table of logarithms, got by assuming n equals 2, n equals 5, n equals 10, and so on, up to n equals 10,000. Open bracket 1 plus 1 half close bracket to the power 2 equals 2.25. Open bracket 1 plus 1 fifth close bracket to the power 5 equals 2.488. Open bracket 1 plus 1 tenth close bracket to the power 10 equals 2.594. Open bracket 1 plus 1 20th close bracket to the power 20 equals 2.653. Open bracket 1 plus 1 over 100 close bracket to the power 100 equals 2.705. Open bracket 1 plus 1 over 1000 close bracket to the power of 1000 equals 2.7169. 1 plus 1 over 10,000 close bracket to the power 10,000 equals 2.7181. It is, however, worthwhile to find another way of calculating this immensely important figure. Accordingly, we will avail ourselves of the binomial theorem and expand the expression open bracket 1 plus 1 over n close bracket to the power n in that well-known way. The binomial theorem gives the rule that open bracket a plus b close bracket to the power n equals a to the n plus n choose 1 times a to the power n minus 1 times b plus n choose 2 times a to the power n minus 2b squared plus n choose 3 times a to the power n minus 3b cubed plus etc. Putting a equals 1 and b equals 1 over n, we get open bracket 1 plus 1 over n close bracket to the power n equals 1 plus 1 plus n choose 2 times 1 over n squared plus n choose 3 times 1 over n cubed plus n choose 4 times 1 over n to the power 4, and so on. Now if we suppose n to become indefinitely great, say a billion or a billion billions, then n minus 1, n minus 2, and n minus 3, etc. will all be sensibly equal to n, and then the series becomes epsilon equals 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial, etc. By taking this rapidly convergent series to as many terms as we please, we can work out the sum to any desired point of accuracy. Here is the working for 10 terms. 1.000000. Dividing by 1, we get the same thing, 1 followed by a decimal point and 6 zeros. Dividing by 2, we get 0 followed by a decimal point, then a 5 and 5 zeros. Dividing by 3, 0.166667. Dividing by 4, 0.041667. Dividing by 5, 0.008333. Dividing by 6, 0.001389. Dividing by 7, 0.000198. Divided by 8, 0.000025. And finally, dividing by 9, 0.000002. And when we add these numbers up, the total becomes 2.718281. Epsilon is incommensurable with 1 and resembles pi in being an interminable non-recurrent decimal. The exponential series. We shall have need of yet another series. Let us again, making use of the binomial theorem, expand the expression open bracket 1 plus 1 over n close bracket to the power n times x, which is the same as epsilon to the power x when we make n indefinitely great. epsilon to the power x equals 1 to the power nx plus nx choose 1 times 1 over n plus nx choose 2 times 1 over n squared plus nx choose 3 times 1 over n cubed plus and so on. When this is expanded without simplifying, 1 plus x plus 1 over 2 factorial multiplied by the fraction in the numerator n squared x squared minus nx, and in the denominator n squared plus the next term 1 over 3 factorial multiplied by the fraction in the numerator n cubed x cubed minus 3n squared x squared plus 2nx divided by in the denominator n cubed plus and so on equals 1 plus x plus the fraction in the numerator x squared minus x over n, and in the denominator 2 factorial plus the fraction in the numerator x cubed minus 3x squared over n plus 2x over n squared divided by in the denominator 3 factorial plus etc. But when n is made infinitely great, this simplifies down to the following. E to the x equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial and so on. This series is called the exponential series. The great reason why epsilon is regarded of importance is that epsilon to the power x possesses a property not possessed by any other function of x, that when you differentiate its value remains unchanged. In other words, its differential coefficient is the same as itself. This can be seen instantly by differentiating it with respect to x thus. d to the x by dx equals 0 plus 1 plus 2x over 2 factorial plus 3x squared over 3 factorial plus 4x cubed over 4 factorial plus 5x to the fourth over 5 factorial, etc., which equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial, etc., which is exactly the same as the original series. End of section 27. Read by Paul King, Mississauga, Ontario, pjk.scripps.mit.edu/pkj. Section 28 of Calculus Made Easy by Silvanus P. Thompson. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Reading by Paul King, pjk.scripps.mit.edu/pkj. Calculus Made Easy by Silvanus P. Thompson. Chapter 14. On True Compound Interest and the Law of Organic Growth, Part 1b. Now we might have gone to work the other way and said, let's find a function of x such that its differential coefficient is the same as itself. Or, is there any expression involving only powers of x which is unchanged by differentiation? Accordingly, let us assume, as a general expression, that y equals a plus bx plus cx squared plus dx cubed plus ex fourth, etc., in which the coefficients a, b, c, d, and e, and so on, will have to be determined, and differentiate it. dy by dx would then equal b plus 2cx plus 3dx squared plus 4ex cubed, etc. Now, if this new expression is really to be the same as that from which it was derived, it is clear that a must equal b, that c equals b over 2, which also equals a over 1 times 2, and that d equals c over 3, which also equals a over 3 factorial, and that e equals d over 4, which is also equal to a over 4 factorial. And the law of change is therefore that y equals a outside the bracket 1 plus x over 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial, and so on, close bracket. If now we take a equals 1 for the sake of further simplicity, we have y equals 1 plus x over 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial, etc. Differentiating it any number of times will give always the same series over and over again. If now we take the particular case of a equals 1 and evaluate the series, we shall get simply when x equals 1, y equals 2.718281, etc. That is, y equals epsilon. When x equals 2, y equals 2.718281, etc. squared, that is, y equals epsilon squared. And when x equals 3, y equals 2.718281, etc. cubed, that is, y equals epsilon cubed. And therefore, when x equals x, y equals 2.71281, etc. to the power x, that is, y equals epsilon to the power x. Thus finally demonstrating that epsilon to the x power plus 1 over 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial, etc. Note how to read exponentials. For the benefit of those who have no tutor at hand, it may be of use to state that epsilon to the power x is read as epsilon to the xth power, or some people read it exponential x. So epsilon to the power pt is read epsilon to the ptth power, or exponential pt. Take some similar expressions. Thus, epsilon to the power minus 2 is read epsilon to the minus 2 power, or exponential minus 2. Epsilon to the power minus ax is read epsilon to the minus axth, or exponential minus ax. Of course, it follows that epsilon to the power y remains unchanged if differentiated with respect to y. Also, epsilon to the power ax, which is equal to open bracket epsilon to the power a close bracket to the power x, will, when differentiated with respect to x, be a multiplied by epsilon to the power ax, because a is a constant. Natural or Naperian logarithms. Another reason why epsilon is important is because it was made by Napier, the inventor of logarithms, the basis of his system. If y is the value of epsilon to the power x, then x is the logarithm to the base epsilon of y. Or if y equals epsilon to the power x, then x equals log base epsilon of y. The two curves plotted in figures 38 and 39 represent these equations. The first curve, figure 38, has the graph plotted by the following xy coordinates. The point x equals 0, y equals 1, the point x equals 0.5, y equals 1.65, the point x equals 1, y equals 2.71, the point x equals 1.5, y equals 4.5, and the point x equals 2, y equals 7.39. For the second graph in figure 39, it possesses the points x equals 0, y equals 1, which you notice is the reverse of the first point of the last graph, x equals 0.69, y equals 2, x equals 1.1, y equals 3, x equals 1.39, y equals 4, x equals 2.08, y equals 8. It will be seen that, though the calculations yield different points for plotting, yet the result is identical. The two equations really mean the same thing. As many persons who use ordinary logarithms, which are calculated to base 10 instead of base epsilon, are unfamiliar with the natural logarithms, it may be worthwhile to say a word about them. The ordinary rule that adding logarithms gives logarithms of the product still holds good, or log base epsilon of a plus log base epsilon of b equals log base epsilon of a times b. Also, the rule of powers holds good, n multiplied by the log base epsilon of a equals log base epsilon of a to the power n. But as 10 is no longer the basis, one cannot multiply by 100 or 1000 by merely adding 2 or 3 to the index. One can change the natural logarithm to the ordinary logarithm simply by multiplying it by 0.4343, or log base 10 of x equals 0.4343 log base epsilon of x, and conversely log base epsilon of x equals 2.3026 multiplied by log base 10 of x. A useful table of Neperian logarithms, also called natural logarithms or hyperbolic logarithms. Natural log of 1, 0. Natural log of 1.1, 0.0953. Natural log of 1.2, 0.1823. Natural log of 1.5, 0.4055. Natural log of 1.7, 0.5306. Natural log of 2.0, 0.6931. Natural log of 2.2, 0.7885. Natural log of 2.5, 0.9163. Natural log of 2.7, 0.9933. Natural log of 2.8, 1.0296. Natural log of 3.0, 1.0986. Natural log of 3.5, 1.2528. Natural log of 4.0, 1.3863. Natural log of 4.5, 1.5041. Natural log of 5.0, 1.6094. Natural log of 6, 1.7918. Natural log of 7, 1.9459. Natural log of 8, 2.0794. Natural log of 9, 2.1972. Natural log of 10, 2.3026. Natural log of 20, 2.9957. Natural log of 50, 3.9120. Natural log of 100, 4.6052. Natural log of 200, 5.2983. Natural log of 500, 6.2146. Natural log of 1000, 6.9078. Natural log of 2000, 7.6009. Natural log of 5000, 8.5172. Natural log of 10,000, 9.2103. Natural log of 20,000, 9.9035. Exponential and logarithmic equations. Now let us try our hands at differentiating certain expressions that contain logarithms or exponentials. Take the equation y equals log base epsilon x. First transform this into epsilon to the power y equals x. Whence, since the differential of epsilon to the power y with regard to y is the original function unchanged, dx by dy equals epsilon to the power y. And reverting from the inverse to the original function, dy by dx equals 1 over dx by dy equals 1 over e to the power y equals 1 over x. Now this is a very curious result. It may be written d of log base epsilon x by dx equals x to the power minus 1. Note that x to the minus 1 is a result that we could never have got by the rule for differentiating powers. That rule is to multiply by the power and reduce the power by 1. Thus differentiating x cubed gave us 3x squared, and differentiating x squared gave us 2x to the power 1. But differentiating x to the 0 does not give us x to the power minus 1, or 0 times x to the power minus 1, because x to the power 0 is itself 1 and is a constant. We shall have to come back to this curious fact that differentiating log base epsilon x gives us 1 over x when we reach the chapter on integrating. Now try to differentiate y equals log base epsilon of the binomial x plus a. That is, e to the power y equals x plus a. We have d of x plus a by dy equals epsilon to the power y. Since the differential of epsilon to the power y remains epsilon to the power y, this gives dx by dy equals epsilon to the power y equals x plus a. Hence, reverting to the original function, we get dy by dx equals 1 over dx by dy equals 1 over x plus a. Next try y equals log base 10 of x. First change to natural logarithms by multiplying by the modulus 0.4343. This gives us y equals 0.4343 log base epsilon of x, whence dy by dx equals 0.4343 divided by x. The next thing is not quite so simple. Try this. Y equals a to the power x. Taking the logarithm of both sides, we get log base epsilon y equals x multiplied by log base epsilon of a. So x equals log base epsilon of y divided by log base epsilon of a, which equals 1 over log base epsilon a multiplied by log base epsilon y. Since 1 over log base epsilon a is a constant, we get dx by dy, which equals 1 over log base epsilon of a multiplied by 1 over y equals 1 over open bracket a to the power x times log base epsilon of a close bracket. Hence, reverting to the original function, dy by dx equals 1 over dx by dy equals a to the x multiplied by log base epsilon a. We see that since dx by dy multiplied by dy by dx equals 1 and dx by dy equals 1 over y multiplied by 1 over log base epsilon a, 1 over y multiplied by dy by dx equals log base epsilon a. We shall find that whenever we have an expression such as log base epsilon y equals a function of x, we always have 1 over y multiplied by dy by dx equals the differential coefficient of the function of x, so that we could have written it at once from log base epsilon y equals x multiplied by log base epsilon of a. 1 over y dy by dx equals log base epsilon a, and dy by dx equals a to the x multiplied by log base epsilon of a. Let us now attempt further examples. Example 1. Y equals epsilon to the power negative ax. Let negative ax equal z, then y equals epsilon to the power z. dy by dx equals epsilon to the power z. dz by dx equals negative a. Hence, dy by dx equals negative a epsilon to the power negative ax. Or thus, log base epsilon to the power y equals negative ax. 1 over y multiplied by dy by dx equals negative a. dy by dx equals negative ay equals negative a epsilon to the power negative ax. Example 2. Y equals epsilon raised to the power x squared over 3. Let x squared over 3 equal z, then y equals epsilon to the power z. dy by dz is epsilon to the power z. dz by dx equals 2x over 3. dy by dx equals 2x over 3 multiplied by epsilon raised to the power x squared over 3. Or thus, log base epsilon of y equals x squared over 3. 1 over y dy by dx equals 2x over 3. dy by dx equals 2x over 3 multiplied by epsilon raised to the power of x squared over 3. Example 3. Y equals epsilon raised to the power 2x over x plus 1. Log base epsilon of y equals 2x over x plus 1. 1 over y dy by dx equals, in the numerator, 2 times open bracket x plus 1 close bracket minus 2x. In the denominator, open bracket x plus 1 close bracket raised to the power 2. Hence, dy by dx equals the fraction 2 divided by open bracket x plus 1 close bracket raised to the power 2, and the fraction is multiplied by epsilon raised to the fraction 2x divided by open bracket x plus 1 close bracket. Check by writing 2x divided by open bracket x plus 1 close bracket equals z. Example 4. Y equals epsilon raised to the square root of the quantity open bracket x squared plus a close bracket. Log base epsilon of y equals open bracket x squared plus a close bracket raised to the power of 1/2. 1 over y dy by dx equals x divided by open bracket x squared plus a close bracket raised to the power of 1/2. And dy by dx equals the fraction in the numerator x multiplied by epsilon raised to the square root x squared plus a divided by, in the denominator, open bracket x squared plus a close bracket raised to the power of 1/2. For if open bracket x squared plus a close bracket raised to the power of 1/2 equals u and x squared plus a equals v, then u equals v to the 1/2. du by dv equals 1 over 2v to the 1/2. dv by dx equals 2x, du by dx equals x in the numerator divided by, in the denominator, open bracket x squared plus a close bracket to the power of 1/2. Check by writing square root of the quantity x squared plus a equals z. Example 5. Y equals log open bracket a plus x cubed. Let a plus x cubed equal z. Then y equals log base epsilon of z. dy by dz equals 1 over z. dz by dx equals 3x squared. Hence dy by dx equals 3x squared divided by the quantity a plus x cubed. Example 6. Y equals log base epsilon open bracket 3x squared plus the square root of the quantity a plus x squared close bracket. Let 3x squared equals the square root of the quantity a plus x squared equals z, then y equals log base epsilon of z. dy by dz equals 1 over z. dz by dx equals 6x plus the fraction in the numerator x divided by the denominator the square root of the quantity x squared plus a. dy by dx equals, in the numerator, open bracket 6x plus the fraction x divided by square root of open bracket x plus a close bracket n numerator divided by the denominator 3x squared plus the square root of open bracket a plus x squared close bracket n denominator. All of this equals, in the numerator, x times open bracket 1 plus 6 times the square root of the quantity x squared plus a n square root n numerator divided by the denominator open bracket 3x squared plus the square root of open bracket x squared plus a close bracket times the square root of the quantity x squared plus a and denominator. Example 7. Y equals open bracket x plus 3 close bracket raised to the power 2 multiplied by the square root of open bracket x minus 2 close bracket. We start with log base epsilon of y equals 2 log base epsilon of the quantity open bracket x plus 3 close bracket plus 1/2 log base epsilon of the quantity open bracket x minus 2 close bracket. 1 over y dy by dx, and that equals 2 over x plus 3 plus 1 over 2 times x minus 2. dy by dx equals open bracket x plus 3 close bracket raised to the power 2 multiplied by the square root of the quantity x minus 2 multiplied by open bracket in the numerator 2 divided by, in the denominator, open bracket x plus 3 close bracket plus, in the numerator, 1 divided by, in the denominator, 2 times open bracket x minus 2 close bracket and close bracket for the expression. Example 8. y equals open bracket x squared plus 3 close bracket to the power 3 multiplied by open bracket x cubed minus 2 close bracket to the power of 2/3. The log base epsilon of y equals 3 log base epsilon of the quantity open bracket x squared plus 3 close bracket plus 2/3 multiplied by log base epsilon open bracket x cubed minus 2 close bracket. 1 over y dy by dx equals 3 times 2x divided by open bracket x squared plus 3 plus 2/3 multiplied by the fraction in the numerator 3x squared divided by in the denominator open bracket x cubed minus 2 close bracket equals 6x divided by open bracket x squared plus 3 close bracket plus 2x squared divided by open bracket x cubed minus 2 close bracket. For if y equals log base epsilon of the quantity open bracket x squared plus 3 close bracket, then x squared plus 3 equals z and u equals log base epsilon of z. Thus du by dz equals 1 over z, dz by dx equals 2x, du by dx equals 2x divided by the quantity open bracket x squared plus 3 close bracket. Similarly, if v equals log base epsilon open bracket x cubed minus 2 close bracket, dv by dx equals 3x squared divided by open bracket x cubed minus 2 close bracket, and dy by dx equals open bracket x squared plus 3 close bracket cubed times open bracket x cubed minus 2 close bracket to the power of 2/3, all multiplied by open bracket 6x divided by open bracket x squared plus 3 close bracket plus 2x squared divided by open bracket x cubed minus 2 close bracket close bracket. Example 9. Y equals the square root of open bracket x squared plus a close bracket divided by the cube root of open bracket x cubed minus a close bracket. Log base epsilon of y equals 1/2 multiplied by log base epsilon of open bracket x squared plus a close bracket minus 1/3 log base epsilon open bracket x cubed minus a close bracket. 1 over y dy by dx equals 1/2 multiplied by the fraction 2x over open bracket x squared plus a close bracket minus 1/3 multiplied by the fraction 3x squared in the numerator divided by in the denominator open bracket x cubed minus a close bracket equals x over open bracket x squared plus a close bracket minus x squared divided by open bracket x cubed minus a close bracket. And dy by dx equals the square root of the quantity open bracket x squared plus a close bracket divided by the cube root of the quantity open bracket x cubed minus a close bracket, all multiplied by open bracket x over open bracket x squared plus a close bracket minus x squared divided by open bracket x cubed minus a close bracket close bracket. Example 10. Y equals 1 divided by log base epsilon of x. dy by dx equals in the numerator open bracket log base epsilon of x times 0 minus 1 times 1 over x close bracket divided by log squared base epsilon of x equals -1 divided by x log squared base epsilon of x. Example 11. Y equals cube root of log base epsilon x equals log base epsilon of x to the power of 1/3. Let z equal log base epsilon of x and y equals z to the 1/3. dy by dz equals 1/3 z to the negative 2/3. dz by dx equals 1 over x. dy by dx equals 1 over 3x multiplied by the cube root of the square of the base epsilon log of x. Example 12. Y equals 1 over a to the x all to the power of a times x. Log base epsilon of y equals ax multiplied by open bracket log base epsilon of 1 minus log base epsilon of a to the x close bracket equals negative ax times the base epsilon log of a to the x. 1 over y dy by dx equals negative ax times a to the x times log base epsilon of a minus a times log base epsilon of a to the x. dy by dx equals negative 1 over a to the x to the power of ax multiplied by open bracket x times a to the x plus 1 times log base epsilon of a plus a times log base epsilon of a to the x. Close bracket. End of part 28. Reading by Paul King, pjk.scripts@mit.edu/pkj. Section 29 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Paul King, Mississauga, Ontario. pjk.scripts.mit.edu/pkj. Calculus Made Easy by Silvanus P. Thompson, Section 29. Exercises 12. Question 1. Differentiate y equals b times, open bracket, epsilon to the exponent ax, take away epsilon to the exponent negative ax, close bracket. Answer: ab multiplied by, open bracket, epsilon to the exponent ax plus epsilon to the exponent negative ax, close bracket. Question 2. Find the differential coefficient with respect to t of the expression u equals at squared plus 2 times the natural log of t. Answer: 2at plus 2 over t. Question 3. If y equals n to the power t, find d of natural log of y by dt. Answer: the natural log of n. Question 4. Show that if y equals 1 over b times a to the power bx divided by the natural log of a, then dy by dx equals a to the bx. Question 5. If w is pv to the power n, find dw by dv. Answer: npv to the power n minus 1. Question 6. Differentiate y equals the natural log of x to the n. Answer: n over x. Question 7. Differentiate y equals 3 times epsilon to the power negative x over x minus 1. Answer: 3 times epsilon to the power of negative x over x minus 1, all divided by the quantity x minus 1 all squared. Question 8. Differentiate y equals the quantity 3x squared plus 1 multiplied by epsilon to the power of negative 5x. Answer: 6x times epsilon to the power negative 5x, subtract 5 times the quantity 3x squared plus 1, close bracket, times epsilon to the power negative 5x. Question 9. Differentiate y equals the natural log of the quantity x to the a plus a. Answer: ax to the power a minus 1, all divided by x to the a plus a. Question 10. Differentiate y equals the quantity 3x squared minus 1 times the quantity root x plus 1. Answer: open bracket, the fraction 6x over the quantity 3x squared minus 1 plus the fraction 1 over 2 times the quantity root x plus x, close bracket, multiplied by the binomial 3x squared minus 1 times the binomial root x plus 1. Question 11. Differentiate the natural log of x plus 3 all divided by x plus 3. Answer: the quantity 1 minus natural log of x plus 3 all divided by x plus 3 quantity squared. Question 12. Differentiate y equals a to the x times x to the a. Answer: a to the x times the quantity open bracket a times x to the a minus 1 plus x to the a times the natural log of a, close bracket. Question 13. It was shown by Lord Kelvin that the speed of signaling through a submarine cable depends on the value of the ratio of the external diameter of the core to the diameter of the enclosed copper wire. If this ratio is called y, then the number of signals s that can be sent per minute can be expressed by the formula s equals a times y squared times the natural log of 1 over y, where a is a constant depending on the length and the quality of the materials. Show that if these are given, s will be a maximum if y equals 1 divided by the square root of epsilon. No answer was given to this problem. Question 14. Find the maximum or minimum of y equals x cubed minus the natural log of x. Answer: minimum y equals 0.7 for x equals 0.694. Question 15. Differentiate y equals the natural log of the quantity a times x times epsilon to the power x. Answer: the quantity 1 plus x divided by x. Question 16. Differentiate y equals the quantity open bracket natural log of ax close bracket all to the power 3. Answer: 3 over x times open bracket the natural log of ax close bracket to the power 2. End of section 29. Reading by Paul King. pjk.scripts.mit.edu/pkj.
Section 30 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Calculus Made Easy by Silvanus P. Thompson. Chapter 14. On True Compound Interest and the Law of Organic Growth. Part 2. The Logarithmic Curve. Let us return to the curve which has its successive ordinates in geometrical progression, such as that represented by the equation y equals bp to the x power. We can see, by putting x equals 0, that b is the initial height of y. Then, when x equals 1, y equals bp, x equals 2, y equals bp squared, x equals 3, y equals bp to the third power, etc. Also, we see that p is the numerical value of the ratio between the height of any ordinate and that of the next preceding it. In Figure 40, we have taken p as 6 over 5, each ordinate being 6/5 as high as the preceding one. If two successive ordinates are related together, thus, in a constant ratio, their logarithms will have a constant difference, so that if we should plot out a new curve, Figure 41, with values of log base epsilon of y as ordinates, it would be a straight line sloping up by equal steps. In fact, it follows from the equation that log base epsilon of y equals log base epsilon of b plus x times log base epsilon of p, whence log base epsilon of y minus log base epsilon of b equals x times log base epsilon of p. Now, since log base epsilon of p is a mere number and may be written as log base epsilon of p equals a, it follows that log base epsilon of y over b equals ax, and the equation takes the new form, y equals b epsilon to the ax power. End of section 30. Section 31 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Calculus Made Easy by Silvanus P. Thompson. Chapter 14. On True Compound Interest and the Law of Organic Growth, Part 3. The die-away curve. If we were to take p as a proper fraction, less than unity, the curve would obviously tend to sink downwards, as in Figure 42, where each successive ordinate is 3/4 of the height of the preceding one. The equation is still y equal bp to the x power, but since p is less than 1, log base epsilon of p will be a negative quantity, and may be written negative a, so that p equal epsilon to the negative a power. And now our equation for the curve takes the form y equal b epsilon to the negative ax power. The importance of this expression is that in the case where the independent variable is time, the equation represents the course of a great many physical processes in which something is gradually dying away. Thus, the cooling of a hot body is represented, in Newton's celebrated law of cooling, by the equation theta sub t equals theta sub 0 epsilon to the negative at power, where theta sub 0 is the original excess of temperature of a hot body over that of its surroundings, theta sub t the excess of temperature at the end of time t, and a is a constant, namely, the constant of decrement depending on the amount of surface exposed by the body, and on its coefficients of conductivity and emissivity, etc. A similar formula, uppercase Q sub t equals uppercase Q sub 0 epsilon to the negative at power, is used to express the charge of an electrified body originally having a charge Q sub 0, which is leaking away with a constant of decrement a, which constant depends in this case on the capacity of the body and on the resistance of the leakage path. Oscillations given to a flexible spring die out after a time, and the dying out of the amplitude of the motion may be expressed in a similar way. In fact, epsilon to the negative at power serves as a die-away factor for all those phenomena in which the rate of decrease is proportional to the magnitude of that which is decreasing, or where, in our usual symbols, dy over dt is proportional at every moment to the value that y has at that moment. For we have only to inspect the curve, Figure 42 above, to see that, at every part of it, the slope, dy over dx, is proportional to the height, y, the curve becoming flatter as y grows smaller. In symbols thus, y equal b epsilon to the negative ax power, or log base epsilon of y equals log base epsilon of b minus ax log base epsilon of epsilon equals log base epsilon of b minus ax, and, differentiating, 1 over y times dy over dx equals negative a. Hence, dy over dx equal b epsilon to the negative ax power times negative a equal negative ay. Or, in words, the slope of a curve is downward and proportional to y and to the constant a. We should have got the same result if we had taken the equation in the form y equal bp to the x power, for then dy over dx equal bp to the x power times log base epsilon of p. But log base epsilon of p equal negative a, giving us dy over dx equal y times negative a equals negative ay, as before. The time constant. In the expression for the die-away factor, epsilon to negative at power, the quantity a is the reciprocal of another quantity known as the time constant, which we may denote by the symbol uppercase T. Then the die-away factor will be written epsilon to the negative t over uppercase T power, and it will be seen by making t equal uppercase T that the meaning of uppercase T, or of 1 over a, is that this is the length of time which it takes for the original quantity, called theta sub 0 or q sub 0 in the preceding instances, to die away 1 over epsilon part, that is, to 0.3678 of its original value. The value of epsilon to the x power and epsilon to the negative x power are continually required in different branches of physics, and as they are given in very few sets of mathematical tables, some of the values are tabulated on page 157 for convenience. As an example of the use of this table, suppose there is a hot body cooling, and that at the beginning of the experiment, that is, when T equals 0, it is 72 degrees hotter than the surrounding objects, and if the time constant of its cooling is 20 minutes, that is, if it takes 20 minutes for its excess of temperature to fall to 1 over epsilon part of 72 degrees, then we can calculate to what it will have fallen in any given time t. For instance, let t be 60 minutes. Then t over uppercase T equal 60 divided by 20 equal 3. And we shall have to find the value of epsilon to the negative 3, and then multiply the original 72 degrees by this. The table shows that epsilon to the negative 3 power is 0.0498, so that at the end of 60 minutes the excess of temperature will have fallen to 72 degrees times 0.0498 equals 3.586 degrees. The values tabulated on page 157. When x is 0.00, epsilon to the x power is 1.0000, epsilon to the negative x power 1.0000, 1 minus epsilon to the negative x power 0.000. When x is 0.10, epsilon to the x power is 1.1052, epsilon to the negative x power 0.9048, 1 minus epsilon to the negative x power 0.0952. When x is 0.20, epsilon to the x power is 1.2214, epsilon to the negative x power is 0.8187, 1 minus epsilon to the negative x power 0.1813. When x is 0.50, epsilon to the x power is 1.6487, epsilon to the negative x power 0.6065, 1 minus epsilon to the negative x power 0.3935. When x is 0.75, epsilon to the x power is 2.1170, epsilon to the negative x power 0.4724, 1 minus epsilon to the negative x power 0.5276. When x is 0.90, epsilon to the x power is 2.4596. Epsilon to the negative x power is 0.4066. 1 minus epsilon to the negative x power is 0.5934. When x is 1.00, epsilon to the x power is 2.7183. Epsilon to the negative x power is 0.3679. 1 minus epsilon to the negative x power 0.6321. When x is 1.10, epsilon to the x power is 3.0042. Epsilon to the negative x power is 0.3329. 1 minus epsilon to the negative x power is 0.6671. When x is 1.20, epsilon to the x power is 3.3201. Epsilon to the negative x power is 0.3012. 1 minus epsilon to the negative x power is 0.6988. When x is 1.25, epsilon to the x power is 3.4903. Epsilon to the negative x power is 0.2865. 1 minus epsilon to the negative x power is 0.7135. When x is 1.50, epsilon to the x power is 4.4817. Epsilon to the negative x power is 0.2231. 1 minus epsilon to the negative x power is 0.7769. When x is 1.75, epsilon to the x power is 5.755. Epsilon to the negative x power is 0.1738. 1 minus epsilon to the negative x power is 0.8262. When x is 2.0, epsilon to the x power is 7.389. Epsilon to the negative x power is 0.1353. 1 minus epsilon to the negative x power is 0.8647. When x is 2.50, epsilon to the x power is 12.182. Epsilon to the negative x power is 0.0821. 1 minus epsilon to the negative x power is 0.9179. When x is 3.0, epsilon to the x power is 20.086. Epsilon to the negative x power is 0.0498. 1 minus epsilon to the negative x power is 0.9502. When x is 3.50, epsilon to the x power is 33.115. Epsilon to the negative x power is 0.0302. 1 minus epsilon to the negative x power is 0.9698. When x is 4.00, epsilon to the x power is 54.598. Epsilon to the negative x power is 0.0183. 1 minus epsilon to the negative x power is 0.9817. When x is 4.50, epsilon to the x power is 90.017. Epsilon to the negative x power is 0.0111. 1 minus epsilon to the negative x power is 0.9889. When x is 5.0, epsilon to the x power is 148.41. Epsilon to the negative x power is 0.0067. 1 minus epsilon to the negative x power is 0.9933. When x is 5.50, Epsilon to the x power is 244.69. Epsilon to the negative x power is 0.0041. 1 minus epsilon to the negative x power is 0.9959. When x is 6.00, epsilon to the x power is 403.43. Epsilon to the negative x power is 0.00248. 1 minus epsilon to the negative x power is 0.99752. When x is 7.50, epsilon to the x power is 1808.04. Epsilon to the negative x power is 0.00055. 1 minus epsilon to the negative x power is 0.99947. When x equals 10, epsilon to the x power is 22,026.5. Epsilon to the negative x power is 0.000045. 1 minus epsilon to the negative x power is 0.999955. Further examples. 1. The strength of an electric current in a conductor at a time t seconds after the application of the electromotive force producing it is given by the expression C equal E over R, open brace, 1 minus epsilon to the negative RT over L power, close brace. The time constant is L over R. If E equal 10, R equal 1, L equals 0.01, then when t is very large, the term epsilon to the negative RT over L power becomes 1, and C equals E over R equals 10. Also, L over R equals T equals 0.01. Its value at any time may be written. C equals 10 minus 10 epsilon to the negative t over 0.01 power, the time constant being 0.01. This means that it takes 0.01 seconds for the variable term to fall by 1 over epsilon equals 0.3678 of its initial value, 10 epsilon to the negative 0 over 0.01 power, equals 10. To find the value of the current when t equals 0.001 seconds, say t over T equals 0.1, epsilon to the negative 0.1 power equal 0.9048 from table. It follows that after 0.001 second, the variable term is 0.9048 times 10 equal 9.048, and the actual current is 10 minus 9.048 equal 0.952. Similarly, at the end of 0.1 seconds, t over T equals 10, epsilon to the negative 10 power equals 0.000045. The variable term is 10 times 0.000045 equals 0.00045, the current being 9.9995. 2. The intensity of I of a beam of light which has passed through a thickness L centimeters of some transparent medium is I equals I sub 0 epsilon to the negative KL power, where I sub 0 is the initial intensity of the beam, and K is a constant of absorption. This constant is usually found by experiments. If it be found, for instance, that a beam of light has its intensity diminished by 18% in passing through 10 centimeters of a certain transparent medium, this means that 82 equals 100 times epsilon to the negative uppercase K times 10 power, or epsilon to the negative 10 uppercase K power equals 0.82. And from the table one sees that 10 uppercase K equals 0.20, very nearly. Hence, uppercase K equals 0.02. To find the thickness that will reduce the intensity to half its value, one must find the value of L, which satisfies the equality 50 equal 100 times epsilon to the negative 0.02 L power, or 0.5 equal epsilon to the negative 0.02 L power. It is found by putting this equation in its logarithmic form, namely, log 0.5 equal negative 0.02 times L times log epsilon, which gives L equal negative 0.3010 over negative 0.02 times 0.4343 equal 34.7 centimeters nearly. 3. The quantity uppercase Q of a radioactive substance which has not yet undergone transformation is known to be related to the initial quantity uppercase Q sub 0 of the substance by the relation uppercase Q equal uppercase Q sub 0 epsilon to the negative lambda t power, where lambda is a constant and t the time in seconds elapsed since the transformation began. For radium uppercase A, if time is expressed in seconds, experiment shows that lambda equal 3.85 times 10 to the negative 3 power. Find the time required for transforming half the substance. This time is called the mean life of the substance. We have 0.5 equal epsilon to the negative 0.00385 t. Log 0.5 equal negative 0.00385 t times log epsilon, and t equal 3 minutes very nearly. End of section 31. Section 32 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Calculus Made Easy by Silvanus P. Thompson. Section 32. Exercises 13. 1. Draw the curve y equal b epsilon to the negative t over uppercase T, where b equals 12, uppercase T equal 8, and t is given various values from 0 to 20. Answer. Let t over uppercase T equal x, therefore t equal 8x, and use the table on page 157. 2. If a hot body cools so that in 24 minutes its excess of temperature has fallen to half the initial amount, deduce the time constant and find how long it will be in cooling down to 1% of the original excess. Answer. T equals 34.627, 159.46 minutes. 3. Plot the curve y equals 100 times the quantity 1 minus epsilon to the negative 2t power. Answer. Take 2t equal x and use the table on page 157. 4. The following equations give very similar curves. 1. Y equal ax over x plus b. 2. Y equal A times the quantity 1 minus epsilon to the negative x over b power. 3. Y equal A over 90-degree arctangent of x over b. Draw all three curves, taking A equal 100 millimeters, B equals 30 millimeters. 5. Find the differential coefficient of y with respect to x if a. Y equals x to the x power, b. Y equals the quantity to the x power of epsilon to the x power, c. Y equals epsilon to the x power to the x power. Answer. A. X to the x power times the quantity 1 plus log base epsilon of x. B. 2x times the quantity to the x power of epsilon to the x power. C. Epsilon to the x power to the x power times x to the x power times the quantity 1 plus the log base epsilon of x. 6. For thorium uppercase A, the value of lambda is 5. Find the mean life, that is, the time taken by the transformation of a quantity uppercase Q of thorium uppercase A equal to half the initial quantity uppercase Q sub 0 in the expression. Q equal Q sub 0 epsilon to the negative lambda t, t being in seconds. Answer. 0.14 seconds. 7. A condenser of capacity uppercase K equals 4 times 10 to the negative 6 power. Charge to a potential of uppercase V sub 0 equals 20 is discharging through a resistance of 10,000 ohms. Find the potential uppercase V after A. 0.1 seconds, B. 0.01 second, assuming that the fall of potential follows the rule uppercase V equals uppercase V sub 0 epsilon to the negative t over uppercase K uppercase R power. Answer. A. 1.642, B. 15.58. 8. The charge uppercase Q of an electrified insulated metal sphere is reduced from 20 to 16 units in 10 minutes. Find the coefficient mu of leakage if uppercase Q equals uppercase Q sub 0 times epsilon to the negative mu t power. Q sub 0 being the initial charge and t being in seconds. Hence find the time taken by half the charge to leak away. Answer. Mu equals 0.00037, 31 to the m power, times 1/4. 9. The dampening on a telephone line can be ascertained from the relation I equals I sub 0 epsilon to the negative beta L, where I is the strength, after t seconds, of a telephonic current of initial strength, I sub 0. L is the length of the line in kilometers, and beta is a constant. For the Franco-English submarine cable laid in 1910, beta equaled 0.0114. Find the dampening at the end of the cable, 40 kilometers, and the length along which I is still 8% of the original current. Limiting value of very good audition. Answer. I is 63.4% of I sub 0, 220 kilometers. 10. The pressure P of the atmosphere at an altitude h kilometers is given by P equals P sub 0 epsilon to the negative kh power. P sub 0 being the pressure at sea level, 760 millimeters, the pressure at 10, 20, and 50 kilometers being 199.2, 42.2, 0.32 respectively, find K in each case. Using the mean value of k, find the percentage error in each case. Answer: 0.133, 0.145, 0.155, mean 0.144, negative 10.2%, negative 0.9%, positive 77.2%. 11. Find the minimum or maximum of y equals x to the x power. Answer: minimum for x equals 1 over epsilon. 12. Find the minimum or maximum of y equals x to the 1 over x power. Answer: maximum for x equals epsilon. 13. Find the minimum or maximum of y equals xa to the 1 over x power. Answer: minimum for x equals log base epsilon of a. End of section 32.
Section 33 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Son of the Exiles. Calculus Made Easy by Silvanus P. Thompson. Chapter 15. How to deal with sines and cosines. Greek letters being usual to denote angles, we will take as the usual letter for any variable angle the letter theta. Let us consider the function y equals sine theta. What we have to investigate is the value of d sine theta over d theta, or in other words, if the angle theta varies, we have to find the relation between the increment of the sine and the increment of the angle, both increments being indefinitely small in themselves. Examine figure 43, wherein, if the radius of the circle is unity, the height of y is the sine and theta is the angle. Now, if theta is supposed to increase by the addition to it of the small angle d theta, an element of angle, the height of y, the sine, will be increased by a small element dy. The new height, y plus dy, will be the sine of the new angle theta plus d theta, or, stating it as an equation, y plus dy equals sine of the sum of theta plus d theta, and subtracting from this the first equation gives dy equals sine of the sum of theta plus d theta minus sine theta. The quantity on the right-hand side is the difference between two sines, and books on trigonometry tell us how to work this out. For they tell us that if m and n are two different angles, sine m minus sine n equals 2 multiplied by the cosine of the quantity m plus n over 2 multiplied by the sine of the quantity m minus n over 2. If then we put m equals theta plus d theta for one angle and n equals theta for the other, we may write dy equals 2 multiplied by the cosine of the quantity theta plus d theta plus theta over 2 multiplied by the sine of the quantity theta plus d theta minus theta over 2. Or dy equals 2 multiplied by the cosine of the quantity theta plus 1/2 d theta multiplied by the sine of 1/2 d theta. But if we regard d theta as indefinitely small, then in the limit we may neglect half d theta by comparison with theta, and may also take sine half d theta as being the same as half d theta. The equation then becomes dy equals 2 times cosine theta times 1/2 d theta. dy equals cosine theta times d theta. And finally, dy over d theta equals cosine theta. The accompanying curves, figures 44 and 45, show, plotted to scale, the values of y equals sine theta and dy over d theta equals cosine theta for the corresponding values of theta. Take next the cosine. Let y equals cosine theta. Now cosine theta equals the sine of the quantity pi over 2, that fraction minus theta. Therefore, dy equals d of the sine of the quantity pi over 2, that fraction minus theta, which equals the cosine of the quantity pi over 2, that fraction minus theta, that cosine multiplied by d negative theta, which equals the cosine of the quantity pi over 2, that fraction minus theta, that cosine multiplied by negative d theta. dy over d theta equals negative cosine of the quantity pi over 2, that fraction minus theta, and it follows that dy over d theta equals negative sine theta. Lastly, take the tangent. Let y equal tangent theta. dy equals the tangent of the quantity theta plus d theta, that tangent minus tangent theta. Expanding, as shown in books on trigonometry, the tangent of the quantity theta plus d theta equals the fraction, the numerator is tangent theta plus tangent d theta, the denominator is 1 minus the multiple of tangent theta and tangent d theta. Whence dy equals the fraction, the numerator is tangent theta plus tangent d theta, the denominator is 1 minus the multiple of tangent theta and tangent d theta, that fraction minus tangent theta, which equals the fraction, the numerator is 1 plus tangent squared theta, that addition multiplied by tangent d theta, the denominator is 1 minus the multiple of tangent theta and tangent d theta. Now remember that if d theta is indefinitely diminished, the value of tangent d theta becomes identical with d theta, and tangent theta multiplied by d theta is negligibly small compared with 1, so that the expression reduces to dy equals the fraction, the numerator is 1 plus tangent squared theta, that addition multiplied by d theta, the denominator is 1. So that dy over d theta equals 1 plus tangent squared theta, or dy over d theta equals secant squared theta. Collecting these results, we have y, dy over d theta, sine theta, cosine theta, cosine theta minus sine theta, tangent theta, secant squared theta. Sometimes in mechanical and physical questions, as for example in simple harmonic motion and in wave motions, we have to deal with angles that increase in proportion to the time. Thus, if T be the time of one complete period or movement round the circle, then since the angle all round the circle is 2 pi radians or 360 degrees, the amount of angle moved through in time t will be theta equals 2 times pi times the fraction t over T in radians. Theta equals 360 times t over T in degrees. If the frequency, or number of periods per second, be denoted by n, then n equals 1 over T, and we may then write theta equals 2 pi n t. Then we shall have y equals the sine of the multiple of 2 pi n t. If now we wish to know how the sine varies with respect to time, we must differentiate with respect not to theta but to t. For this we must resort to the artifice explained in chapter 9, page 66, and put dy over d t equals dy over d theta times d theta over d t. Now d theta over d t will obviously be 2 pi n, so that dy over d t equals cosine theta times 2 pi n, which equals 2 pi n times the cosine of 2 pi n t. Similarly, it follows that d cosine of 2 pi n t over d t equals negative 2 pi n multiplied by the sine of 2 pi n small t. End of section 33. Recording by Son of the Exiles.
Section 34 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Eelme. Calculus Made Easy by Silvanus P. Thompson. Chapter 15. How to Deal with Sines and Cosines, Part 2. Second differential coefficient of sine or cosine. We have seen that when sine theta is differentiated with respect to theta, it becomes cos theta, and that when cos theta is differentiated with respect to theta, it becomes minus sine theta, or, in symbols, d squared of sine theta over d theta squared is equal to minus sine theta. So we have this curious result that we have found a function such that if we differentiate it twice over, we get the same thing from which we started, but with the sign changed from plus to minus. The same thing is true for the cosine. For differentiating cos theta gives us minus sine theta, and differentiating minus sine theta gives us minus cos theta, or thus d squared cos theta over d theta squared is equal to minus cos theta. Sines and cosines are the only functions of which the second differential coefficient is equal and of opposite sign to the original function. Examples. With what we have so far learned, we can now differentiate expressions of a more complex nature. 1. Y is equal to arcsine x. If y is the arc whose sine is x, then x equals sine y. Dx over dy is equal to cos y. Passing now from the inverse function to the original one, we get dy over dx is equal to 1 over dx over dy, which is equal to 1 over cos y. Now, cos y is equal to 1 minus the square root of 1 minus sine squared y, which is equal to the square root of 1 minus x squared. Hence, dy over dx is equal to 1 over square root of 1 minus x squared. A rather unexpected result. 2. Y is equal to cos cubed theta. This is the same as y is equal to cos theta cubed. Let cos theta be equal to v, then y be equal to v cubed. Dy over dv is 3v squared. dv over d theta is equal to minus sine theta, and dy over d theta is equal to dy over dv times dv over d theta, which is equal to minus 3 cos squared theta sine theta. 3. Y is equal to sine brackets x plus a close brackets. Let x plus a be equal to v, then y is equal to sine of v. dy over dv is equal to cos v. dv over dx is equal to 1, and dy over dx is equal to cos of open brackets x plus a close brackets. 4. Y is equal to log base e of sine theta. Let sine theta be equal to v, y equal to log base e of v, then dy over dv is equal to 1 over v, and dv over d theta is equal to cos theta. dy over d theta is equal to 1 over sine theta times cos theta, which is equal to cotangent of theta. 5. Y is equal to cotangent of theta, which is equal to cos theta over sine theta. dy over d theta is equal to minus sine squared theta minus cos squared theta divided by sine squared theta is equal to minus, open brackets, 1 plus cot squared theta, close brackets, which is equal to minus cosecant squared theta. 6. Y is equal to tan 3 theta. Let 3 theta be equal to v, y be equal to tan v, and dy over dv be equal to secant square of v. dv over d theta is equal to 3. dy over d theta is equal to 3 secant squared of 3 theta. 7. Y is equal to square root of 1 plus 3 tan squared of theta. Y is equal to 1 plus 3 tan squared theta in brackets to the power of 1/2. Let 3 tan squared theta be equal to v. Y is equal to open brackets 1 plus v close brackets to the power of 1/2. dy over dv is equal to 1 over 2 square root of 1 plus v. See page 67. dv over d theta is equal to 6 tan theta secant squared theta. For if tan theta is equal to u, v is equal to 3u squared, dv over du is equal to 6u, du over d theta is equal to secant squared of theta. Hence, dv over d theta is equal to 6 open brackets tan theta secant squared theta close brackets. Hence, dy over d theta is equal to 6 tan theta secant squared theta over 2 times the square root of 1 plus 3 tan squared theta. 8. Y is equal to sine x cos x. dy over dx is equal to sine x times minus sine x plus cos x times cos x, which is equal to cos squared x minus sine squared x. End of section 34. Recording by Eelme.
Section 35 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Calculus Made Easy by Silvanus P. Thompson. Section 35. Exercises 14. 1. Differentiate the following. 1. Y equal a sine of the quantity theta minus pi over 2. 2. Y equal sine squared theta and y equal sine 2 theta. 3. Y equal sine cubed of theta and y equal sine of 3 theta. Answer. 1. dy over d theta equals a cosine of the quantity theta minus pi over 2. 2. dy over d theta equals 2 sine of theta cosine of theta equals sine of 2 theta and dy over d theta equal 2 cosine 2 theta. 3. dy over d theta equal 3 sine squared theta cosine theta and dy over d theta equal 3 cosine 3 theta. 2. Find the value of theta for which sine theta times cosine theta is a maximum. Answer. Theta equals 45 degrees, or pi over 4 radians. 3. Differentiate y equal 1 over 2 pi times cosine 2 pi nt. Answer. dy over dt equal negative n sine 2 pi nt. 4. If y equal sine a to the x power, find dy over dx. Answer. A to the x power log base epsilon of a cosine a to the x power. 5. Differentiate y equal log to base epsilon of cosine x. Answer. Cosine x over sine x equal cotan x. 6. Differentiate y equal 18.2 sine of the quantity x plus 26 degrees. Answer. 18.2 cosine of the quantity x plus 26 degrees. 7. Plot the curve y equal 100 sine the quantity theta minus 15 degrees and show that the slope of the curve at theta equals 75 degrees is half the maximum slope. Answer. The slope is dy over d theta equal 100 cosine of the quantity theta minus 15 degrees, which is a maximum when the quantity theta minus 15 degrees equals 0 or theta equals 15 degrees. The value of the slope being then equal 100. When theta equals 75 degrees, the slope is 100 cosine the quantity 75 degrees minus 15 degrees equals 100 cosine of 60 degrees equals 100 times 1/2 equal 50. 8. If y equals sine theta times sine 2 theta, find dy over d theta. Answer. Cosine theta sine 2 theta plus 2 cosine 2 theta sine theta equals 2 sine theta of the quantity cosine squared theta plus cosine 2 theta equals 2 sine theta of the quantity 3 cosine squared theta minus 1. 9. If y equal a times the tangent to the m power of theta to the n power, find the differential coefficient of y with respect to theta. Answer. amn theta to the n minus 1 power, tangent to the m minus 1 power of theta to the n power, secant squared theta to the n power. 10. Differentiate y equal epsilon to the x power sine squared of x. Answer. Epsilon to the x power times the quantity sine squared x plus sine 2x. Epsilon to the x power times the quantity sine squared x plus 2 sine 2x plus 2 cosine 2x. 11. Differentiate the three equations of exercises 13, number 4, and compare their differential coefficients as to whether they are equal or nearly equal for very small values of x, or for very large values of x, or for values of x in the neighborhood of x equal 30. Answers. 1. dy over dx equal ab over the quantity squared x plus b. 2. A over b times epsilon to the negative x over b power. 3. 1 over 90 degrees times ab over the quantity b squared plus x squared. 12. Differentiate the following. 1. Y equal secant x. 2. Y equal arc cosine x. 3. Y equal arctangent x. 4. Y equal arcsecant x. 5. Y equal tangent x times the square root of 3 secant x. Answers. 1. dy over dx equal secant x tangent x. 2. dy over dx equal negative 1 over the square root of 1 minus x squared. 3. dy over dx equal 1 over 1 plus x squared. 4. dy over dx equal 1 over x times the square root of x squared minus 1. 5. dy over dx equal the square root of 3 secant x times the quantity 3 secant squared x minus 1 all over 2. 13. Differentiate y equals sine of the quantity to the 2.3 power of 2 theta plus 3. Answer. dy over d theta equals 4.6 times the quantity to the 1.3 power of 2 theta plus 3, cosine of the quantity to the 2.3 power of 2 theta plus 3. 14. Differentiate y equals sine of the quantity to the 2.3 power of 2 theta plus 3. Answer. dy over d theta equals 4.6 times the quantity to the 1.3 power of 2 theta plus 3, cosine of the quantity to the 2.3 power of 2 theta plus 3. 14. Differentiate y equal theta cubed plus 3 sine of the quantity theta plus 3 minus 3 to the sine theta power minus 3 to the theta power. Answer. dy over d theta equals 3 theta squared plus 3 cosine of the quantity theta plus 3 minus log base epsilon of 3 times the quantity cosine theta times 3 to the sine theta power plus 3 theta. 15. Find the maximum or minimum of y equal theta cosine theta. Answer. Theta equals cotangent theta. Theta equals plus or minus 0.86 is maximum for positive theta, minimum for negative theta. End of section 35.
Section 36 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Calculus Made Easy by Silvanus P. Thompson. Chapter 16, Partial Differentiation, Part 1. We sometimes come across quantities that are functions of more than one independent variable. Thus, we may find a case where y depends on two other variable quantities, one of which we will call u and the other v. In symbols, y equals f open brackets u, v close brackets. Take the simplest concrete case. Let y equals u times v. What are we to do? If we were to treat v as a constant and differentiate with respect to u, we should get dy subscript v equals v du, or if we treat u as a constant and differentiate with respect to v, we should have dy subscript u equals u dv. The little letters here put as subscripts are to show which quantity has been taken as constant in the operation. Another way of indicating that the differentiation has been performed only partially, that is, has been performed only with respect to one of the independent variables, is to write the differential coefficients with Greek deltas, like delta instead of little d. In this way, delta y over delta u equals v, and delta y over delta v equals u. If we put in these values for v and u respectively, we shall have dy subscript v equals delta y over delta u du, and dy subscript u equals delta y over delta v dv, which are partial differentials. But, if you think of it, you will observe that the total variation of y depends on both these things at the same time. That is to say, if both are varying, the real dy ought to be written dy equals delta y over delta u du add delta y over delta v dv, and this is called a total differential. In some books it is written dy equals open brackets dy over du close brackets du add open brackets dy over dv close brackets dv. Example 1. Find the partial differential coefficients of the expression w equals 2ax squared add 3bxy add 4cy cubed. The answers are delta w over delta x equals 4ax add 3by, and delta w over delta y equals 3bx add 12cy squared. The first is obtained by supposing y constant, the second is obtained by supposing x constant. Then dw equals open brackets 4ax add 3by close brackets dx add open brackets 3bx add 12cy squared close brackets dy. Example 2. Let z equals x to the power of y. Then, treating first y and then x as constant, we get in the usual way delta z over delta x equals y times x to the power of y minus 1, and delta z over delta y equals x to the power of y times log base e x, so that dz equals y times x to the power of y minus 1 dx, add x to the power of y log base e x dy. Example 3. A cone having height h and radius of base r has volume v equals 1/3 pi r squared h. If its height remains constant, while r changes, the ratio of change of volume with respect to radius is different from the ratio of change of volume with respect to height which would occur if the height were varied and the radius kept constant, for delta v over delta r equals 2 pi over 3 rh. Delta v over delta h equals pi over 3 r squared. The variation when both the radius and the height change is given by dv equals 2 pi over 3 times rh dr, add pi over 3 times r squared dh. Example 4. In the following example, big F and little f denote two arbitrary functions of any form whatsoever. For example, they may be sine functions, or exponentials, or mere algebraic functions of the two independent variables t and x. This being understood, let us take the expression y equals big F open brackets x add at close brackets add little f open brackets x minus at close brackets, or y equals big F as a function of w add little f as a function of v, where w equals x add at and v equals x minus at. Then delta y over delta x equals delta big F as a function of w over delta w times delta w over delta x add delta little f as a function of v over delta v times delta v over delta x equals big F as a function of w prime times 1 add little f as a function of v prime times 1, where the figure 1 is simply the coefficient of x in w and v, and delta squared y over delta x squared equals big F as a function of w double primed add little f as a function of v double primed. Also, delta y over delta t equals delta big F as a function of w over delta w times delta w over delta t add delta little f as a function of v over delta v times delta v over delta t equals big F as a function of w primed times a minus little f as a function of v primed times a, and delta squared y over delta t squared equals big F as a function of w double primed times a squared add little f as a function of v double primed times a squared, whence delta squared y over delta t squared equals a squared delta squared y over delta x squared. This differential equation is of immense importance in mathematical physics. End of section 36. Section 37 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Calculus Made Easy by Silvanus P. Thompson. Chapter 16, Partial Differentiation, Part 2. Maxima and minima of functions of two independent variables. Example 5. Let us take up again exercise 9, page 107, number 4. Let x and y be the length of two of the portions of the string. The third is 30 minus open brackets x add y close brackets, and the area of the triangle is a equals the square root of s open brackets s minus x close brackets open brackets s minus y close brackets open brackets s minus 30 plus x plus y close brackets, where s is the half perimeter 15, so that a equals the square root of 15p, where p equals open brackets 15 minus x close brackets open brackets 15 minus y close brackets open brackets x add y minus 15 close brackets equals xy squared add x squared y minus 15x squared minus 15y squared minus 45xy add 450x add 450y minus 3375. Clearly a is maximum when p is maximum. dp equals delta p over delta x dx add delta p over delta y dy. For a maximum, clearly it will not be a minimum in this case, one must have simultaneously delta p over delta x equals 0 and delta p over delta y equals 0. That is, 2xy minus 30x add y squared minus 45y add 450 equals 0, and 2xy minus 30y add x squared minus 45x add 450 equals 0. An immediate solution is x equals y. If we now introduce this condition in the value of p, we find p equals open brackets 15 minus x close brackets squared open brackets 2x minus 15 close brackets equals 2x cubed minus 75x squared add 900x minus 3375. For maximum or minimum, dp over dx equals 6x squared minus 150x add 900 equals 0, which gives x equals 15 or x equals 10. Clearly x equals 15 gives minimum area, x equals 10 gives the maximum, for d2p over dx squared equals 12x minus 150, which is plus 30 for x equals 15 and minus 30 for x equals 10. Example 6. Find the dimensions of an ordinary railway coal truck with rectangular ends, so that for a given volume V, the area of sides and floor together is as small as possible. The truck is a rectangular box open at the top. Let x be the length and y the width, and the depth is v over xy. The surface area is S equals xy add 2v over x add 2v over y. ds equals delta s over delta x dx add delta s over delta y dy equals open brackets y minus 2v over x squared close brackets dx add open brackets x minus 2v over y squared close brackets dy. For minimum, clearly it won't be a maximum here. Y minus 2v over x squared equals 0. X minus 2v over y squared equals 0. Here also, an immediate solution is x equals y, so that s equals x squared plus 4v over x. ds over dx equals 2x minus 4v over x squared equals 0 for minimum, and x equals the cube root of 2v. End of section 37. Section 38 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Calculus Made Easy by Silvanus P. Thompson. Section 38. Exercises 15. 1. Differentiate the expression x cubed over 3 minus 2x cubed y minus 2y squared x add y over 3 with respect to x alone and with respect to y alone. Answer. X squared minus 6x squared y minus 2y squared. 1/3 minus 2x cubed minus 4xy. 2. Find the partial differential coefficients with respect to x, y and z of the expression x squared yz plus xy squared z plus xyz squared plus x squared y squared z squared. Answer. 2xyz add y squared z add z squared y add 2xy squared z squared. 2xyz add x squared z add x z squared add 2x squared y z squared. 2xyz add x squared y add x, y squared, add 2x squared, y squared, z. 3. Let r squared equals open brackets x minus a close brackets squared, add open brackets y minus b close brackets squared, add open brackets z minus c close brackets squared. Find the value of delta r over delta x, add delta r over delta y, add delta r over delta z. Also find the value of delta squared r over delta x squared, add delta squared r over delta y squared, add delta squared r over delta z squared. Answer 1 over r, open brackets x minus a close brackets, add open brackets y minus b close brackets, add open brackets z minus c close brackets, equals open brackets x add y add z close brackets minus open brackets a add b add c close brackets all over r. 3 over r. 4. Find the total differential of y equals u to the power of v. Answer. dy equals v u to the power of v minus 1 du, add u to the power of v log base e u dv. 5. Find the total differential of y equals u cubed sin v of y equals open brackets sin x close brackets to the power of u, and of y equals log base e u all over v. Answer. dy equals 3 sin v u squared du, add u cubed cos v dv. dy equals u sin x to the power of u minus 1 cos x dx, add open brackets sin x close brackets to the power of u log base e sin x du. dy equals 1 over v times 1 over u du minus log base e u times 1 over v squared dv. 6. Verify that the sum of three quantities x, y, z, whose product is a constant k, is maximum when these three quantities are equal. 7. Find the maximum or minimum of the function u equals x add 2xy add y. Answer. Minimum for x equals y equals minus a half. 8. The Post Office regulations state that no parcel is to be of such a size that its length plus its girth exceeds 6 feet. What is the greatest volume that can be sent by post? A. In the case of a package of rectangular cross section. B. In the case of a package of circular cross section. Answer. A. Length 2 feet, width equals depth equals 1 foot. Volume equals 2 cubic feet. B. Radius equals 2 over pi feet equals 7.46 inches. Length equals 2 feet. Volume equals 2.54. 9. Divide pi into 3 parts such that the continued product of their signs may be a maximum or minimum. Answer. All 3 parts equal, the product is maximum. 10. Find the maximum or minimum of u equals e to the power of x add y all over xy. Answer. Minimum for x equals y equals 1. 11. Find the maximum and minimum of u equals y add 2x minus 2 log base ey minus log base ex. Answer. Minimum, x equals a half and y equals 2. 12. A Telfordge bucket of given capacity has the shape of a horizontal isosceles triangular prism, with the apex underneath and the opposite face open. Find its dimensions in order that the least amount of iron sheet may be used in its construction. Answer. Angle at apex equals 90 degrees. Equal sides equals length equals the cube root of 2v. End of section 38.
Section 39 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Bruce Kachuk. Calculus Made Easy by Silvanus P. Thompson. Chapter 17, Integration, Part 1. The great secret has already been revealed that this mysterious symbol, the integral sign, which is, after all, only a long S, merely means the sum of, or the sum of all such quantities as. It therefore resembles that other symbol, the Greek sigma, which is also a sign of summation. There is this difference, however, in the practice of mathematical men as to the use of these signs, that while sigma is generally used to indicate the sum of a number of finite quantities, the integral sign is generally used to indicate the summing up of a vast number of small quantities of indefinitely minute magnitude, mere elements, in fact, that go to make up the total required. Thus, integral dy equals y, and integral dx equals x. Anyone can understand how the whole of anything can be conceived of as made up of a lot of little bits, and the smaller the bits, the more of them there will be. Thus, a line 1 inch long may be conceived as made up of 10 pieces, each 1/10 of an inch long, or of 100 parts, each part being 1/100th of an inch long, or of 1,000,000 parts, each of which is 1/1,000,000th of an inch long. Or, pushing the thought to the limits of conceivability, it may be regarded as made up of an infinite number of elements, each of which is infinitesimally small. Yes, you will say, but what is the use of thinking of anything that way? Why not think of it straight off, as a whole? The simple reason is that there are a vast number of cases in which one cannot calculate the bigness of the thing as a whole without reckoning up the sum of a lot of small parts. The process of integrating is to enable us to calculate totals that otherwise we should be unable to estimate directly. Let us first take one or two simple cases to familiarize ourselves with this notion of summing up a lot of separate parts. Consider the series 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus 1/64 plus etc. Here, each member of the series is formed by taking it half the value of the preceding. What is the value of the total if we could go on to an infinite number of terms? Every schoolboy knows that the answer is 2. Think of it, if you like, as a line. Begin with 1 inch, add a ½ inch, add a quarter, add an eighth, and so on. If at any point of the operation we stop, there will still be a piece wanting to make up the whole 2 inches, and the piece wanting will always be the same size as the last piece added. Thus, if after having put together 1, 1/2, and 1/4, we stop, there will be 1/4 wanting. If we go on till we have added 1/64th, there will still be 1/64th wanting. The remainder needed will always be equal to the last term added. By an infinite number of operations only should we reach the actual 2 inches. Practically, we should reach it when we got to pieces so small that they could not be drawn. That would be after about 10 terms, for the 11th term is 1/1024th. If we want to go so far that not even a Whitworth's measuring machine would detect it, we should merely have to go to about 20 terms. A microscope would not show even the 18th term. So the infinite number of operations is no such dreadful thing after all. The integral is simply the whole lot. But, as we shall see, there are cases in which the integral calculus enables us to get at the exact total that there would be as the result of an infinite number of operations. In such cases, the integral calculus gives us a rapid and easy way of getting at a result that would otherwise require an interminable lot of elaborate working out. So we had best lose no time in learning how to integrate. End of section 39. Section 40 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Bruce Kachuk. Calculus Made Easy by Silvanus P. Thompson. Chapter 17. Integration, Part 2. Slopes of curves and the curves themselves. Let us make a little preliminary inquiry about the slopes of curves, for we have seen that differentiating a curve means finding an expression for its slope, or for its slopes at different points. Can we perform the reverse process of reconstructing the whole curve if the slope or slopes are prescribed for us? Go back to case 2 on page 82. Here we have the simplest of curves, a sloping line with the equation y equals ax plus b. We know that here b represents the initial height of y when x equals 0, and that a, which is the same as dy over dx, is the slope of the line. The line has a constant slope. All along it, the elementary triangles have the same proportion between height and base. Suppose we were to take the dx's and dy's of finite magnitude so that 10 dx's made up 1 inch. Then there would be 10 little triangles. Now suppose that we were ordered to reconstruct the curve, starting merely from the information that dy over dx equals a. What could we do? Still taking the little d's as of finite size, we could draw 10 of them, all with the same slope, and then put them together end to end, like this. And, as the slope is the same for all, they would join to make, as in figure 48, a sloping line, sloping with the correct slope dy over dx equals a. And whether we take the dy's and dx's as finite or infinitely small, as they are all alike, clearly y over x equals a, if we reckon y as the total of all the dy's and x as the total of all the dx's. But whereabouts are we to put this sloping line? Are we to start at the origin, uppercase O, or higher up? As the only information we have is as to the slope, we are without any instructions as to the particular height above uppercase O. In fact, the initial height is undetermined. The slope will be the same, whatever the initial height. Let us therefore make a shot at what may be wanted, and start the sloping line at a height uppercase C above uppercase O. That is, we have the equation y equals ax plus uppercase C. It becomes evident now that in this case the added constant means a particular value that y has when x equals 0. Now let us take a harder case, that of a line the slope of which is not constant, but turns up more and more. Let us assume that the upward slope gets greater and greater in proportion as x grows. In symbols, this is dy over dx equals ax. Or, to give a concrete case, take a equals 1/5, so that dy over dx equals 1/5 x. Then we had best begin by calculating a few of the values of the slope at different values of x, and also draw little diagrams of them. When x equals 0, dy over dx equals 0. X equals 1, dy over dx equals 0.2. X equals 2, dy over dx equals 0.4. X equals 3, dy over dx equals 0.6. X equals 4, dy over dx equals 0.8. X equals 5, dy over dx equals 1.0. Now try to put the pieces together, setting each so that the middle of its base is the proper distance to the right, and so that they fit together at the corners. Thus, figure 49. The result is, of course, not a smooth curve, but it is an approximation to one. If we had taken bits half as long and twice as numerous, like figure 50, we should have a better approximation. But for a perfect curve, we ought to take each dx and its corresponding dy infinitesimally small and infinitely numerous. Then how much ought the value of any y to be? Clearly, at any point P of the curve, the value of y will be the sum of all the little dy's from 0 up to that level. That is to say, integral dy equals y. And as each dy is equal to 1/5 x times dx, it follows that the whole y will be equal to the sum of all such bits as 1/5 x times dx, or as we should write it, integral 1/5 x times dx. Now if x had been constant, integral 1/5 x times dx would have been the same as 1/5 x integral dx, or 1/5 x squared. But x began by being 0 and increases to the particular value of x at the point P, so that its average value from 0 to that point is 1/2 x. Hence, integral 1/5 x dx equals 1/10 x squared, or y equals 1/10 x squared. But, as in the previous case, this requires the addition of an undetermined constant C, because we have not been told at what height above the origin the curve will begin when x equals 0. So we write, as the equation of the curve drawn in figure 51, y equals 1/10 x squared plus C. End of section 40. Section 41 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Bruce Kachuk. Calculus Made Easy by Silvanus P. Thompson. Section 41. Exercises 16. 1. Find the ultimate sum of 2/3 plus 1/3 plus 1/6 plus 1/12 plus 1/24 plus etc. Answer: 1 1/3. 3. If log to the base epsilon of the quantity 1 plus x equals x minus the quantity x squared over 2 plus the quantity x cubed over 3 minus the quantity x to the 4th over 4 plus etc., find log to the base epsilon of 1.3. Answer: 0.2624. 4. Following a reasoning similar to that explained in this chapter, find y. A. If dy over dx equals 1/4 x. B. If dy over dx equals cosine x. Answers: A. Y equals 1/8 x squared plus C. B. Y equals sine x plus C. 5. If dy over dx equals 2x plus 3, find y. Answer: y equals x squared plus 3x plus C. End of section 41. Section 42 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Bruce Kachuk. Calculus Made Easy by Silvanus P. Thompson. Chapter 18. Integrating as the reverse of differentiating. Part 1. Differentiating is the process by which, when y is given us as a function of x, we can find dy over dx. Like every other mathematical operation, the process of differentiation may be reversed. Thus, if differentiating y equals x to the 4th gives us dy over dx equals 4x cubed, if one begins with dy over dx equals 4x cubed, one would say that reversing the process would yield y equals x to the fourth. But here comes in a curious point. We should get dy over dx equals 4x cubed if we had begun with any of the following: x to the fourth, or x to the fourth plus a, or x to the fourth plus c, or x to the fourth with any added constant. So it is clear that in working backwards from dy over dx to y, one must make provision for the possibility of there being an added constant, the value of which will be undetermined until ascertained in some other way. So, if differentiating x to the n power yields nx to the n minus 1 power, going backwards from dy over dx equals nx to the n minus 1 power, will give us y equals x to the n power plus uppercase C, where uppercase C stands for the yet undetermined possible constant. Clearly, in dealing with powers of x, the rule for working backwards will be increase the power by 1, then divide by that increased power and add the undetermined constant. So, in the case where dy over dx equals x to the n power, working backwards, we get y equals the quantity 1 over n plus 1, n quantity, times x to the n plus 1 power, plus uppercase C. If differentiating the equation y equals ax to the n power gives us dy over dx equals anx to the n minus 1 power, it is a matter of common sense that beginning with dy over dx equals anx to the n minus 1 power and reversing the process will give us y equals ax to the n power. So when we are dealing with a multiplying constant, we must simply put the constant as a multiplier of the result of the integration. Thus, if dy over dx equals 4x squared, the reverse process gives us y equals 4/3 x cubed. But this is incomplete, for we must remember that if we had started with y equals ax to the n power plus uppercase C, where uppercase C is any constant quantity whatever, we should equally have found dy over dx equals anx to the n minus 1 power. So therefore, when we reverse the process, we must always remember to add on this undetermined constant, even if we do not yet know what its value will be. This process, the reverse of differentiating, is called integrating, for it consists in finding the value of the whole quantity y when you are given only an expression for dy, or for dy over dx. Hitherto, we have as much as possible kept dy and dx together as a differential coefficient. Henceforth, we shall more often have to separate them. If we begin with a simple case, dy over dx equals x squared, we may write this, if we like, as dy equals x squared dx. Now this is a differential equation, which informs us that an element of y is equal to the corresponding element of x multiplied by x squared. Now what we want is the integral. Therefore, write down with the proper symbol the instructions to integrate both sides. Thus, integral dy equals integral x squared dx. We haven't yet integrated, we have only written down instructions to integrate. If we can, let us try. Plenty of other fools can do it, why not we also? The left-hand side is simplicity itself. The sum of all the bits of y is the same thing as y itself. So we may at once put y equals integral x squared dx. But when we come to the right-hand side of the equation, we must remember that what we have got to sum up together is not all the dx's, but all such terms as x squared dx. And this will not be the same as x squared integral dx, because x squared is not a constant. For some of the dx's will be multiplied by big values of x squared, and some will be multiplied by small values of x squared, according to what x happens to be. So we must bethink ourselves as to what we know about this process of integration being the reverse of differentiation. Now, our rule for this reversed process, when dealing with x to the nth power, is increase the power by 1 and divide by the same number as this increased power. That is to say, x squared dx will be changed to 1/3 x cubed. Footnote: you may ask, what has become of the little dx at the end? Well, remember that it was really part of the differential coefficient, and when changed over to the right-hand side, as in the x squared dx, serves as a reminder that x is the independent variable with respect to which the operation is to be effected, and, as a result of the product being totaled up, the power of x has increased by 1. You will soon become familiar with all this. End of footnote. Put this into the equation, but don't forget to add the constant of integration, uppercase C, at the end. So we get y equals 1/3 x cubed plus uppercase C. You have actually performed the integration. How easy! Let us try another simple case. Let dy over dx equal ax to the 12th, where a is any constant multiplier. Well, we found when differentiating that any constant factor in the value of y reappeared unchanged in the value of dy over dx. In the reversed process of integrating, it will therefore also reappear in the value of y. So we may go to work as before. Thus, dy equals ax to the 12th times dx. Integral dy equals integral ax to the 12th times dx. Integral dy equals a integral x to the 12th dx. Y equals a times 1/13 x to the 13th plus uppercase C. So that is done. How easy! We begin to realize now that integrating is a process of finding our way back, as compared with differentiating. If ever, during differentiating, we have found any particular expression, in this example, ax to the 12th, we can find our way back to the y from which it was derived. The contrast between the two processes may be illustrated by the following remark due to a well-known teacher. If a stranger were set down in Trafalgar Square and told to find his way to Euston Station, he might find the task hopeless. But if he had previously been personally conducted from Euston Station to Trafalgar Square, it would be comparatively easy to him to find his way back to Euston Station. End of section 42. Section 43 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Bruce Kachuk. Calculus Made Easy by Silvanus P. Thompson. Chapter 18. Integrating as the reverse of differentiating, Part 2. Integration of the sum or difference of two functions. Let dy over dx equal x squared plus x cubed. Then dy equals x squared dx plus x cubed dx. There is no reason why we should not integrate each term separately, for we found that when we differentiated the sum of two separate functions, the differential coefficient was simply the sum of the two separate differentiations. So when we work backwards, integrating, the integration will be simply the sum of the two separate integrations. Our instructions will then be integral dy equals integral of the quantity x squared plus x cubed dx equals integral x squared dx plus integral x cubed dx. Y equals 1/3 x cubed plus 1/4 x to the 4th plus uppercase C. If either of the terms had been a negative quantity, the corresponding term in the integral would have also been negative, so that differences are as readily dealt with as sums. End of section 43. Section 44 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Bruce Kachuk. Calculus Made Easy by Silvanus P. Thompson. Chapter 18. Integrating as a reverse of differentiating. Part 3. How to deal with constant terms. Suppose there is, in the expression to be integrated, a constant term, such as this. dy over dx equals x to the nth plus b. This is laughably easy, for you have only to remember that when you differentiated the expression y equals ax, the result was dy over dx equals a. Hence, when you work the other way and integrate, the constant reappears, multiplied by x. So we get dy equals x to the nth dx plus b times dx. Integral dy equals integral x to the nth dx plus integral b dx. Y equals 1 over n plus 1 all times x to the n plus 1 power plus bx plus uppercase C. Here are a lot of examples on which to try your newly acquired powers. Examples. 1. Given dy over dx equals 24 x to the 11th, find y. Answer. Y equals 2x to the 12th plus uppercase C. 2. Find the integral of the quantity a plus b times the quantity x plus 1 dx. It is the quantity a plus b integral the quantity x plus 1 dx. Or, open parenthesis, a plus b, close parenthesis, open bracket, integral x dx plus integral dx, close bracket, or, open parenthesis, a plus b, close parenthesis, open parenthesis, the quantity x squared over 2, end quantity, plus x, close parenthesis, plus uppercase C. 3. Given du over dt equals gt to the 1/2 power, find u. Answer. U equals 2/3 gt to the 3 over 2 power, plus uppercase C. 4. dy over dx equals x cubed minus x squared plus x. Find y. dy equals, open parenthesis, x cubed minus x squared plus x, close parenthesis, dx. Or dy equals x cubed dx minus x squared dx plus x dx. Y equals integral x cubed dx minus integral x squared dx plus integral x dx. And y equals 1/4 x to the 4th minus 1/3 x cubed plus 1/2 x squared plus uppercase C. 5. Integrate 9.75x to the 2.25 power dx. Answer. Y equals 3x to the 3.25 power plus uppercase C. All these are easy enough. Let us try another case. Let dy over dx equal ax to the minus 1 power. Proceeding as before, we will write dy equals ax to the minus 1 power times dx. Integral dy equals a integral x to the minus 1 power dx. Well, but what is the integral of x to the minus 1 power dx? If you look back amongst the results of differentiating x squared and x cubed and x to the nth, etc., you will find we never got x to the minus 1 power from any one of them as the value of dy over dx. We got 3x squared from x cubed, we got 2x from x squared, we got 1 from x to the 1 power, that is, from x itself. But we did not get x to the minus 1 power from x to the 0 power for two very good reasons. First, x to the 0 power is simply equal to 1 and is a constant and could not have a differential coefficient. Secondly, even if it could be differentiated, its differential coefficient, got by slavishly following the usual rule, would be 0 times x to the minus 1 power, and that multiplication by 0 gives it 0 value. Therefore, when we now come to try to integrate x to the minus 1 power dx, we see that it does not come in anywhere in the powers of x that are given by the rule. Integral x to the nth dx equals the quantity 1 over n plus 1, end quantity, times x to the n plus 1 power. It is an exceptional case. Well, but try again. Look through all the various differentials obtained from various functions of x, and try to find amongst them x to the minus 1 power. A sufficient search will show that we actually did get dy over dx equals x to the minus 1 power as a result of differentiating the function y equals log base epsilon of x. Then, of course, since we know that differentiating log base epsilon of x gives us x to the minus 1 power, we know that by reversing the process, integrating dy equals x to the minus 1 power dx will give us y equals log base epsilon of x. But we must not forget the constant factor a that was given, nor must we omit to add the undetermined constant of integration. This then gives us as a solution to the present problem y equals a log base epsilon of x plus uppercase C. NB. Here note this very remarkable fact, that we could not have integrated in the above case if we had not happened to know the corresponding differentiation. If no one had found out that differentiating log base epsilon of x gave x to the minus 1 power, we should have been utterly stuck by the problem how to integrate x to the minus 1 power dx. Indeed, it should be frankly admitted that this is one of the curious features of the integral calculus, that you can't integrate anything before the reverse process of differentiating something else has yielded that expression which you want to integrate. No one, even today, is able to find the general integral of the expression dy over dx equals a to the minus x squared power, because a to the minus x squared power has never yet been found to result from differentiating anything else. Another simple case. Find integral of the quantity x plus 1 times quantity x plus 2 dx. On looking at the function to be integrated, you remark that it is the product of two different functions of x. You could, you think, integrate the quantity x plus 1 dx by itself, or the quantity x plus 2 dx by itself. Of course you could, but what to do with a product? None of the differentiations you have learned have yielded you for the differential coefficient a product like this. Failing such, the simplest thing is to multiply up the two functions and then integrate. This gives us integral of the quantity x squared plus 3x plus 2 dx. And this is the same as integral x squared dx plus integral 3x dx plus integral 2 dx. And performing the integrations, we get 1/3 x cubed plus 3 over 2 x squared plus 2x plus uppercase C. End of section 44. Section 45 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Bruce Kachuk. Calculus Made Easy by Silvanus P. Thompson. Chapter 18. Integrating as the reverse of differentiating. Part 4. Some other integrals. Now that we know that integration is the reverse of differentiation, we may at once look up the differential coefficients we already know and see from what functions they were derived. This gives us the following integrals ready-made. X to the minus 1 power. Integral x to the minus 1 power dx equals log base epsilon of x plus uppercase C. 1 over the quantity x plus a, integral 1 over the quantity x plus a and quantity dx equals log base epsilon of the quantity x plus a and quantity plus uppercase C. Epsilon to the x power, integral epsilon to the x power dx equals epsilon to the x power plus uppercase C. Epsilon to the minus x power, integral epsilon to the minus x power dx equals minus epsilon to the minus x power plus uppercase C. For if y equals minus 1 over epsilon to the x power, dy over dx equals minus numerator epsilon to the x power times 0 minus 1 times epsilon to the x power, and numerator all over denominator epsilon to the 2x power, and denominator equals epsilon to the minus x power. Sine x, integral sine x dx equals minus cosine x plus uppercase C. Cosine x, integral cosine x dx equals sine x plus uppercase C. Also, we may deduce the following. Log base epsilon of x, integral log base epsilon of x dx equals x of the quantity log base epsilon of x minus 1 and quantity plus uppercase C. For if y equals x log base epsilon of x minus x, dy over dx equals x over x plus log base epsilon of x minus 1 equals log base epsilon of x. Log base 10 of x, integral log base 10 of x dx equals 0.4343x of the quantity log base epsilon of x minus 1 and quantity plus uppercase C. A to the x power, integral a to the x power dx equals the quantity a to the x power over log base epsilon of a and quantity plus uppercase C. Cosine ax, integral cosine ax dx equals the quantity 1 over a and quantity sine ax plus uppercase C. For if y equals sine ax, dy over dx equals a cosine ax. Hence, to get cosine ax, one must differentiate y equals the quantity 1 over a and quantity sine ax. Sine ax, integral sine ax dx equals minus the quantity 1 over a and quantity cosine ax plus uppercase C. Try also cosine squared theta. A little dodge will simplify matters. Cosine 2 theta equals cosine squared theta minus sine squared theta equals 2 cosine squared theta minus 1. Hence, cosine squared theta equals 1/2 times the quantity cosine 2 theta plus 1, and integral cosine squared theta d theta equals 1/2 integral the quantity cosine 2 theta plus 1 and quantity d theta equals 1/2 integral cosine 2 theta d theta plus 1/2 integral d theta equals the quantity sine 2 theta over 4 and quantity plus the quantity theta over 2 and quantity plus uppercase C. See also the table of standard forms on pages 249 to 251. You should make such a table for yourself, putting in it only the general functions which you have successfully differentiated and integrated. See to it that it grows steadily. End of section 45. Section 46 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Bruce Kachuk. Calculus Made Easy by Silvanus P. Thompson. Chapter 18. Integrating as the reverse of differentiating. Part 5. On double and triple integrals. In many cases, it is necessary to integrate some expression for two or more variables contained in it, and in that case, the sign of integration appears more than once. Thus, integral of function f of x, y, end function dx dy means that some function of the variables x and y has to be integrated for each. It does not matter in which order they are done. Thus, take the function x squared plus y squared. Integrating it with respect to x gives us integral x squared plus y squared dx equals 1/3 x cubed plus xy squared. Now integrate this with respect to y. Integral 1/3 x cubed plus xy squared dy equals 1/3 x cubed y plus 1/3 xy cubed, to which of course a constant is to be added. If we had reversed the order of the operations, the result would have been the same. In dealing with areas of surfaces and of solids, we have often to integrate both for length and breadth, and thus have integrals of the form integral u times dx dy, where u is some property that depends at each point on x and on y. This would then be called a surface integral. It indicates that the value of all such elements as u times dx times dy, that is to say, of the value of u over a little rectangle dx long and dy broad, has to be summed up over the whole length and whole breadth. Similarly, in the case of solids, where we deal with 3 dimensions. Consider any element of volume, the small cube whose dimensions are dx, dy, dz. If the figure of the solid be expressed by the function f of x, y, z, then the whole solid will have the volume integral. Volume equals integral of function f of x, y, z, end function, times dx times dy times dz. Naturally, such integrations have to be taken between appropriate limits in each dimension, and the integration cannot be performed unless one knows in what way the boundaries of the surface depend on x, y, and z. If the limits for x are from x sub 1 to x sub 2, those for y from y sub 1 to y sub 2, and those for z from z sub 1 to z sub 2, then clearly we have volume equals integral from z sub 1 to z sub 2, integral from y sub 1 to y sub 2, integral from x sub 1 to x sub 2 of function f of x, y, z, end function, times dx times dy times dz. There are, of course, plenty of complicated and difficult cases, but in general it is quite easy to see the significance of the symbols where they are intended to indicate that a certain integration has to be performed over a given surface, or throughout a given solid space. End of section 46. Section 47 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Bruce Kachuk. Calculus Made Easy by Silvanus P. Thompson. Section 47. Exercises 17. 1. Find integral y dx when y squared equals 4ax. Answer, numerator 4 times the square root of a times x to the 3 over 2 power, and numerator all over denominator 3, and denominator plus uppercase C. 2. Find integral 3 over x to the 4th power dx. Answer, minus the quantity 1 over x cubed and quantity plus uppercase C. 3. Find integral the quantity 1 over a and quantity x cubed dx. Answer, the quantity x to the 4th power over 4a and quantity plus uppercase C. 4. Find integral of the quantity x squared plus a and quantity dx. Answer, 1/3 x cubed plus ax plus uppercase C. 5. Integrate 5x to the minus 7 over 2 power. Answer, minus 2x to the minus 5 over 2 power plus uppercase C. 6. Find integral of the quantity 4x cubed plus 3x squared plus 2x plus 1 and quantity dx. Answer, x to the 4th power plus x cubed plus x squared plus x plus uppercase C. 7. If dy over dx equals the quantity ax over 2 plus the quantity bx squared over 3 plus the quantity cx cubed over 4, find y. Answer, the quantity ax squared over 4 plus the quantity bx cubed over 9 plus the quantity cx to the 4th power over 16 plus uppercase C. 8. Find integral of the quantity x squared plus a all over x plus a and quantity dx. Answer, x squared plus a all over x plus a equals x minus a plus the quantity a squared plus a all over x plus a and quantity by division. Therefore, the answer is the quantity x squared over 2 and quantity minus ax plus the quantity a squared plus a and quantity log base epsilon of the quantity x plus a and quantity plus uppercase C. 9. Find integral of the quantity x plus 3 and quantity cubed dx. Answer, the quantity x to the 4th power over 4 and quantity plus 3x cubed plus the quantity 27 over 2 and quantity x squared plus 27x plus uppercase C. 10. Find integral of the quantity x plus 2 times the quantity x minus a dx. Answer, the quantity x cubed over 3 plus the quantity 2 minus a over 2 and quantity times x squared minus 2ax plus uppercase C. 11. Find integral of the quantity the square root of x plus the cube root of x and quantity times 3a squared dx. Answer, a squared times the quantity 2x to the 3 over 2 power plus 9 over 4x to the 4 over 3 power and quantity plus uppercase C. 12. Find integral of the quantity sine theta minus 1/2 and quantity d theta over 3. Answer, minus 1/3 cosine theta minus 1/6 theta plus uppercase C. 13. Find integral cosine squared a theta d theta. Answer, theta over 2 plus the quantity sine 2a theta over 4a and quantity plus uppercase C. 14. Find integral sine squared theta d theta. Answer, theta over 2 minus the quantity sine 2 theta over 4 and quantity plus uppercase C. 15. Find integral sine squared a theta d theta. Answer: theta over 2 minus the quantity sine 2a theta over 4a, end quantity, plus uppercase C. 16. Find integral epsilon to the 3x power dx. Answer: 1/3 epsilon to the 3x power, plus uppercase C. 17. Find integral dx over 1 plus x. Answer: log base epsilon of the quantity 1 plus x, end quantity, plus uppercase C. 18. Find integral dx over 1 minus x. Answer: minus log base epsilon of the quantity 1 minus x, end quantity, plus uppercase C. End of section 47. Section 48 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Bruce Kachuk. Calculus Made Easy by Silvanus P. Thompson. Chapter 19. On Finding Areas by Integrating, Part 1. One use of the integral calculus is to enable us to ascertain the values of areas bounded by curves. Let us try to get at the subject bit by bit. Let uppercase AB, figure 52, be a curve, the equation to which is known. That is, y in this curve is some known function of x. Think of a piece of the curve from the point uppercase P to the point uppercase Q. Let a perpendicular uppercase PM be dropped from uppercase P, and another uppercase QN from the point uppercase Q. Then call uppercase OM equals x sub 1 and uppercase ON equals x sub 2, and the ordinates uppercase PM equals y sub 1 and uppercase QN equals y sub 2. We have thus marked out the area uppercase PQNM that lies beneath the piece uppercase PQ. The problem is, how can we calculate the value of this area? The secret of solving this problem is to conceive the area as being divided up into a lot of narrow strips, each of them being of the width dx. The smaller we take dx, the more of them there will be between x sub 1 and x sub 2. Now the whole area is clearly equal to the sum of the areas of all such strips. Our business will then be to discover an expression for the area of any one narrow strip, and to integrate it so as to add together all the strips. Now think of any one of the strips. It will be like this, being bounded between two vertical sides, with a flat bottom dx, and with a slightly curved, sloping top. Suppose we take its average height as being y. Then, as its width is dx, its area will be y dx. And seeing that we may take the width as narrow as we please, if we only take it narrow enough, its average height will be the same as the height at the middle of it. Now let us call the unknown value of the whole area uppercase S, meaning surface. The area of one strip will be simply a bit of the whole area, and may therefore be called d uppercase S. So we may write area of one strip equals d uppercase S equals y times dx. If then we add up all the strips, we get total area uppercase S equals integral d uppercase S equals integral y dx. So then our finding uppercase S depends on whether we can integrate y times dx for the particular case, when we know what the value of y is as a function of x. For instance, if you were told that for the particular curve in question, y equals b plus ax squared, no doubt you could put that value into the expression and say, then I must find integral of the quantity b plus ax squared, end quantity, dx. That is all very well, but a little thought will show you that something more must be done. Because the area we are trying to find is not the area under the whole length of the curve, but only the area limited on the left by uppercase PM and on the right by uppercase QN. It follows that we must do something to define our area between those limits. This introduces us to a new notion, namely that of integrating between limits. We suppose x to vary, and for the present purpose we do not require any value of x below x sub 1, that is uppercase OM, nor any value of x above x sub 2, that is uppercase ON. When an integral is to be thus defined between two limits, we call the lower of the two values the inferior limit, and the upper value the superior limit. Any integral so limited we designate as a definite integral, by way of distinguishing it from a general integral, to which no limits are assigned. In the symbols which give instructions to integrate, the limits are marked by putting them at the top and bottom, respectively, of the sign of integration. Thus the instruction integral from x equals x sub 1 to x equals x sub 2 of y times dx will be read, find the integral of y times dx between the inferior limit x sub 1 and the superior limit x sub 2. Sometimes the thing is written more simply, integral from x sub 1 to x sub 2 of y times dx. Well, but how do you find an integral between limits when you have got these instructions? Look again at figure 52. Suppose we could find the area under the larger piece of curve from uppercase A to uppercase Q, that is from x equals 0 to x equals x sub 2, naming the area uppercase AQNO. Then suppose we could find the area under the smaller piece from uppercase A to uppercase P, that is from x equals 0 to x equals x sub 1, namely the area uppercase APMO. If then we were to subtract the smaller area from the larger, we should have left as a remainder the area uppercase PQNM, which is what we want. Here we have the clue as to what to do. The definite integral between the two limits is the difference between the integral worked out for the superior limit and the integral worked out for the lower limit. Let us then go ahead. First, find the general integral thus, integral y dx. And, as y equals b plus ax squared is the equation to the curve in figure 52, integral of the quantity b plus ax squared and quantity dx is the general integral which we must find. Doing the integration in question by the rule, we get bx plus the quantity a over 3 and quantity times x cubed plus uppercase C. And this will be the whole area from 0 up to any value of x that we may assign. Therefore, the larger area up to the superior limit x sub 2 will be bx sub 2 plus the quantity a over 3 and quantity times x sub 2 cubed plus uppercase C. And the smaller area up to the inferior limit x sub 1 will be bx sub 1 plus the quantity a over 3 and quantity times x sub 1 cubed plus uppercase C. Now subtract the smaller from the larger, and we get for the area uppercase S the value area uppercase S equals b times the quantity x sub 2 minus x sub 1 and quantity plus a over 3 times the quantity x sub 2 cubed minus x sub 1 cubed. This is the answer we wanted. Let us give some numerical values. Suppose b equals 10, a equals 0.06, and x sub 2 equals 8, and x sub 1 equals 6. Then the area uppercase S is equal to 10 times the quantity 8 minus 6 plus 0.06 over 3 times the quantity 8 cubed minus 6 cubed equals 20 plus 0.02 times the quantity 512 minus 216 equals 20 plus 0.02 times 296 equals 20 plus 5.92 equals 25.92. Let us here put down a symbolic way of stating what we have ascertained about limits. Integral from x equals x sub 1 to x equals x sub 2 of y dx equals y sub 2 minus y sub 1, where y sub 2 is the integrated value of y dx corresponding to x sub 2 and y sub 1 that corresponding to x sub 1. All integration between limits requires the difference between two values to be thus found. Also note that, in making the subtraction, the added constant C has disappeared. Examples. 1. To familiarize ourselves with the process, let us take a case of which we know the answer beforehand. Let us find the area of the triangle which has base x equals 12 and height y equals 4. We know beforehand, from obvious mensuration, that the answer will come 24. Now here we have as the curve a sloping line for which the equation is y equals x over 3. The area in question will be integral from x equals 0 to x equals 12 of y times dx equals integral from x equals 0 to x equals 12 of x over 3 times dx. Integrating x over 3 times dx and putting down the value of the general integral in square brackets with the limits marked above and below, we get area equals open bracket 1/3 times 1/2 x squared close bracket from x equals 0 to x equals 12 plus C equals open bracket x squared over 6 close bracket from x equals 0 to x equals 12 plus C equals open bracket 12 squared over 6 close bracket minus open bracket 0 squared over 6 close bracket equals 144 over 6 equals 24, which is the answer. Let us satisfy ourselves about this rather surprising dodge of calculation by testing it on a simple example. Get some squared paper, preferably some that is ruled in little squares of 1/8 inch or 1/10 inch each way. On this squared paper, plot out the graph of the equation y equals x over 3. The values to be plotted will be x equals 0, y equals 0, x equals 3, y equals 1, x equals 6, y equals 2, x equals 9, y equals 3, x equals 12, y equals 4. Now reckon out the area beneath the curve by counting the little squares below the line, from x equals 0 as far as x equals 12 on the right. There are 18 whole squares and 4 triangles, each of which has an area equal to 1 1/2 squares, or in total 24 squares. Hence 24 is the numerical value of the integral of x over 3 dx between the lower limit of x equals 0 and the higher limit of x equals 12. As a further exercise, show that the value of the same integral between the limits of x equals 3 and x equals 15 is 36. 2. Find the area between limits x equals x sub 1 and x equals 0 of the curve y equals b over x plus a. Area equals integral from x equals 0 to x equals x sub 1 of y times dx equals integral from x equals 0 to x equals x sub 1 of b over x plus a dx equals b open bracket log base epsilon of the quantity x plus a close bracket from 0 to x sub 1 plus C equals b open bracket log base epsilon of the quantity x sub 1 plus a minus log base epsilon of the quantity 0 plus a, close bracket, equals b log base epsilon of the quantity numerator x sub 1 plus a over denominator a, which is the answer. NB. Notice that in dealing with definite integrals, the constant uppercase C always disappears by subtraction. Let it be noted that this process of subtracting one part from a larger to find the difference is really a common practice. How do you find the area of a plane ring, the outer radius of which is r sub 2 and the inner radius is r sub 1? You know from mensuration that the area of the outer circle is pi r sub 2 squared. Then you find the area of the inner circle, pi r sub 1 squared. Then you subtract the latter from the former and find area of ring equals pi times the quantity r sub 2 squared minus r sub 1 squared, which may be written pi times the quantity r sub 2 plus r sub 1 times the quantity r sub 2 minus r sub 1 equals mean circumference of ring times width of ring. 3. Here's another case, that of the die-away curve. Find the area between x equals 0 and x equals a of the curve whose equation is y equals b epsilon to the minus x power. Area equals b integral from x equals 0 to x equals a of epsilon to the minus x power times dx. The integration gives equals b open bracket minus epsilon to the minus x power close bracket from 0 to a equals b open bracket the quantity minus epsilon to the minus a power minus the quantity minus epsilon to the minus 0 power close bracket equals b times the quantity 1 minus epsilon to the minus a power. 4. Another example is afforded by the adiabatic curve of a perfect gas, the equation to which is PV to the n power equals C, where P stands for pressure, V for volume, and n is of the value 1.42. Find the area under the curve, which is proportional to the work done in suddenly compressing the gas from volume V sub 2 to volume V sub 1. Here we have area equals integral from V equals V sub 1 to V equals V sub 2 of CV to the minus n power times dV equals C open bracket the quantity 1 over 1 minus n quantity times V to the 1 minus n power close bracket from V sub 1 to V sub 2 equals C times the quantity 1 over 1 minus n quantity times the quantity V sub 2 to the 1 minus n power minus V sub 1 to the 1 minus n power equals the quantity minus C over 0.42 quantity times the quantity 1 over V sub 2 to the 0.42 power minus 1 over V sub 1 to the 0.42 power. An exercise. Prove the ordinary mensuration formula that the area uppercase A of a circle whose radius is uppercase R is equal to pi uppercase R squared. Consider an elementary zone or annulus of the surface of breadth dr situated at a distance r from the center. We may consider the entire surface as consisting of such narrow zones, and the whole area uppercase A will simply be the integral of all such elementary zones from center to margin, that is, integrated from r equals 0 to r equals uppercase R. We have therefore to find an expression for the elementary area d uppercase A of the narrow zone. Think of it as a strip of breadth dr and of a length that is the periphery of the circle of radius r, that is, a length of 2 pi r. Then we have as the area of the narrow zone d uppercase A equals 2 pi r dr. Hence, the area of the whole circle will be uppercase A equals integral d uppercase A equals integral from r equals 0 to r equals uppercase R of 2 pi r times dr equals 2 pi integral from r equals 0 to r equals uppercase R of r times dr. Now the general integral of r times dr is 1/2 r squared. Therefore, uppercase A equals 2 pi, open bracket, 1/2 r squared, close bracket, from r equals 0 to r equals uppercase R. Or, uppercase A equals 2 pi, open bracket, 1/2 uppercase R squared minus 1/2 times 0 squared, close bracket. Whence, uppercase A equals pi uppercase R squared. Another exercise. Let us find the mean ordinate of the positive part of the curve y equals x minus x squared. To find the mean ordinate, we shall have to find the area of the piece uppercase OMN, and then divide it by the length of the base uppercase ON. But before we can find the area, we must ascertain the length of the base, so as to know up to what limit we are to integrate. At uppercase N, the ordinate y has 0 value. Therefore, we must look at the equation and see what value of x will make y equal 0. Now clearly, if x is 0, y will also be 0, the curve passing through the origin uppercase O. But also, if x equals 1, y equals 0, so that x equals 1 gives us the position of the point uppercase N. Then the area wanted is equals integral from x equals 0 to x equals 1 of the quantity x minus x squared dx equals, open bracket, 1/2 x squared minus 1/3 x cubed, close bracket, from 0 to 1 equals, open bracket, 1/2 minus 1/3, close bracket, minus, open bracket, 0 minus 0, close bracket, equals 1/6. But the base length is 1. Therefore, the average ordinate of the curve equals 1/6. NB. It will be a pretty and simple exercise in maxima and minima to find by differentiation what is the height of the maximum ordinate. It must be greater than the average. The mean ordinate of any curve over a range from x equals 0 to x equals x sub 1 is given by the expression mean y equals 1 over x sub 1 integral from x equals 0 to x equals x sub 1 of y times dx. One can also find in the same way the surface area of a solid of revolution. Example. The curve y equals x squared minus 5 is revolving about the axis of x. Find the area of the surface generated by the curve between x equals 0 and x equals 6. A point on the curve, the ordinate of which is y, describes a circumference of length 2 pi y, and a narrow belt of the surface of width dx corresponding to this point has for area 2 pi y dx. The total area is 2 pi integral from x equals 0 to x equals 6 of y dx equals 2 pi integral from x equals 0 to x equals 6 of the quantity x squared minus 5 dx equals 2 pi, open bracket, x cubed over 3 minus 5x, close bracket, from 0 to 6 equals 6.28 times 42 equals 263.76. End of section 48. Section 49 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Bruce Kachuk. Calculus Made Easy by Silvanus P. Thompson. Chapter 19, on finding areas by integrating. Part 2, areas in polar coordinates. When the equation of the boundary of an area is given as a function of the distance r of a point of it from a fixed point O, called the pole, and of the angle which r makes with the positive horizontal direction OX, the process just explained can be applied just as easily, with a small modification. Instead of a strip of area, we consider a small triangle OAB, the angle at O being d theta, and we find the sum of all the little triangles making up the required area. The area of such a small triangle is approximately the quantity A_B over 2 n quantity times r, or the quantity r d theta over 2 n quantity times r. Hence the portion of the area included between the curve and two positions of r, corresponding to the angles theta sub 1 and theta sub 2, is given by 1/2 integral from theta equals theta sub 1 to theta equals theta sub 2 of r squared d theta. Examples. 1. Find the area of the sector of 1 radian in a circumference of radius a inches. The polar equation of the circumference is evidently r equals a. The area is 1/2 integral from theta equals theta sub 1 to theta equals theta sub 2 of a squared d theta equals a squared over 2 integral from theta equals 0 to theta equals 1 of d theta equals a squared over 2. 2. Find the area of the first quadrant of the curve, known as Pascal's snail, the polar equation of which is r equals a times the quantity 1 plus cosine theta. Area equals 1/2 integral from theta equals 0 to theta equals pi over 2 of a squared times the quantity 1 plus cosine theta end quantity squared d theta equals a squared over 2 integral from theta equals 0 to theta equals pi over 2 of the quantity 1 plus 2 cosine theta plus cosine squared theta end quantity d theta equals a squared over 2 open bracket theta plus 2 sine theta plus theta over 2 plus sine 2 theta over 4 close bracket from 0 to pi over 2 equals numerator a squared times the quantity 3 pi plus 8 and numerator over denominator 8. End of section 49. Section 50 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Bruce Kachuk. Calculus Made Easy by Silvanus P. Thompson. Chapter 19, on finding areas by integrating. Part 3, volumes by integration. What we have done with the area of a little strip of a surface, we can, of course, just as easily do with the volume of a little strip of a solid. We can add up all the little strips that make up the total solid and find its volume, just as we have added up all the small little bits that made up an area to find the final area of the figure operated upon. Examples. 1. Find the volume of a sphere of radius r. A thin spherical shell has for volume 4 pi x squared dx. Summing up all the concentric shells which make up the sphere, we have volume sphere equals integral from x equals 0 to x equals r of 4 pi x squared dx equals 4 pi open bracket x cubed over 3, close bracket, from 0 to r, equals 4 over 3 pi r cubed. We can also proceed as follows. A slice of the sphere of thickness dx has for volume pi y squared dx. Also, x and y are related by the expression y squared equals r squared minus x squared. Hence, volume sphere equals 2 integral from x equals 0 to x equals r of pi times the quantity r squared minus x squared and quantity dx equals 2 pi open bracket integral from x equals 0 to x equals r of r squared dx minus integral from x equals 0 to x equals r of x squared dx close bracket equals 2 pi open bracket r squared x minus the quantity x cubed over 3 close bracket from 0 to r equals the quantity 4 pi over 3 and quantity r cubed. 2. Find the volume of the solid generated by the revolution of the curve y squared equals 6x about the axis of x between x equals 0 and x equals 4. The volume of a strip of the solid is pi y squared dx. Hence, volume equals integral from x equals 0 to x equals 4 of pi y squared dx equals 6 pi integral from x equals 0 to x equals 4 of x dx equals 6 pi open bracket x squared over 2 close bracket from 0 to 4 equals 48 pi equals 150.8. End of section 50. Section 51 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Bruce Kachuk. Calculus Made Easy by Silvanus P. Thompson. Chapter 19 on finding areas by integrating. Part 4 on quadratic means. In certain branches of physics, particularly in the study of alternating electric currents, it is necessary to be able to calculate the quadratic mean of a variable quantity. By quadratic mean is denoted the square root of the mean of the squares of all the values between the limits considered. Other names for the quadratic mean of any quantity are its virtual value or its RMS, meaning root mean square value. The French term is valeur efficace. If y is the function under consideration and the quadratic mean is to be taken between the limits of x equals 0 and x equals L, then the quadratic mean is expressed as the square root of the quantity 1 over L integral from 0 to L of y squared dx. Examples. 1. To find the quadratic mean of the function y equals ax. Here the integral is integral from 0 to L of a squared x squared dx, which is 1/3 a squared L cubed. Dividing by L and taking the square root, we have quadratic mean equals the quantity 1 over the square root of 3 and quantity AL. Here the arithmetical mean is 1/2 AL, and the ratio of quadratic to arithmetical mean, this ratio is called the form factor, is 2 over the square root of 3 equals 1.155. 2. To find the quadratic mean of the function y equals x to the a power, the integral is integral from x equals 0 to x equals L of x to the 2a power dx. That is, numerator L to the 2a plus 1 power over denominator 2a plus 1. Hence, quadratic mean equals the square root of the quantity, numerator L to the 2a power over denominator 2a plus 1. 3. To find the quadratic mean of the function y equals a to the x over 2 power. The integral is integral from x equals 0 to x equals L of, open parenthesis, a to the x over 2 power, close parenthesis, squared dx. That is, integral from x equals 0 to x equals L of a to the x power dx. Or, open bracket, a to the x power over log base epsilon of a, close bracket, from x equals 0 to x equals L, which is, numerator, the quantity a to the L power in quantity minus 1 over denominator log base epsilon of a. Hence the quadratic mean is the square root of the quantity, numerator a to the L power minus 1 over denominator L log base epsilon of a. End of section 51.
Section 52 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Calculus Made Easy by Silvanus P. Thompson. Section 52. Exercises 18. 1. Find the area of a curve y equals x squared add x minus 5 between x equals 0 and x equals 6, and the mean ordinates between these limits. Answer. Area equals 60, mean ordinate equals 10. 2. Find the area of the parabola y equals 2a root x between x equals 0 and x equals a. Show that it is 2/3 of the rectangle of the limiting ordinate and of its abscissa. Answer. Area equals 2/3 of a times 2a root a. 3. Find the area of the positive portion of a sine curve and the mean ordinate. Answer. Area equals 2, mean ordinate equals 2 over pi equals 0.637. 4. Find the area of the positive portion of the curve y equals sin squared x and find the mean ordinate. Answer. Area equals 1.57, mean ordinate equals 0.5. 5. Find the area included between the two branches of the curve y equals x squared plus minus x to the power of 5 over 2, from x equals 0 to x equals 1. Also the area of the positive portion of the lower branch of the curve. Answer. 0.572, 0.0476. 6. Find the volume of a cone of radius of base r and of height h. Answer. Volume equals pi r squared h over 3. 7. Find the area of the curve y equals x cubed minus log base ex between x equals 0 and x equals 1. Answer. 1.25. 8. Find the volume generated by the curve y equals the square root of 1 add x squared, as it revolves around the axis of x between x equals 0 and x equals 4. Answer. 79.4. 9. Find the volume generated by a sine curve revolving around the axis of x. Find also the area of its surface. Answer. Volume equals 4.9348. Area of surface equals 12.57 from 0 to pi. 10. Find the area of the portion of the curve xy equals a, included between x equals 1 and x equals a. Find the mean ordinate between these limits. Answer. A log base ea, a over a minus 1 log base EA. 11. Show that the quadratic mean of the function y equals sin x between the limits of 0 and pi radians is root 2 over 2. Find also the arithmetical mean of the same function between the same limits, and show that the form factor is 1.11. 12. Find the arithmetical and quadratic means of the function x squared add 3x add 2 from x equals 0 to x equals 3. Answer. Arithmetical mean 9.5. Quadratic mean 10.85. 13. Find the quadratic mean and the arithmetical mean of the function a1 sin x add a3 sin 3x. Answer. Quadratic mean equals 1 over root 2 times the square root of a1 squared add a3 squared. Arithmetical mean equals 0. The first involves a somewhat difficult integral and may be stated thus. By definition, the quadratic mean will be the square root of 1 over 2 pi integral between 0 and 2 pi open brackets a1 sin x add a3 sin 3x close brackets squared dx. Now the integration indicated by integral open brackets a1 squared sin squared x add 2a1 a3 sin x sin 3x add a3 squared sin squared 3x close brackets dx is more readily obtained if for sin squared x we write 1 minus cos 2x all over 2. For 2 sin x sin 3x we write cos 2x minus cos 4x, and for sin squared 3x 1 minus cos 6x all over 2. Making these substitutions and integrating, we get a1 squared over 2 open brackets x minus sin 2x all over 2 close brackets add a1 a3 open brackets sin 2x all over 2 minus sin 4x all over 4 close brackets add a3 squared over 2 open brackets x minus sin 6x all over 6 close brackets. At the lower limit, the substitution of 0 for x causes all this to vanish, while at the upper limit the substitution of 2 pi for x gives a1 squared pi add a3 squared pi, and hence the answer follows. 14. A certain curve has the equation y equals 3.42 times e to the power of 0.21x. Find the area included between the curve and the axis of x from the ordinate at x equals 2 to the ordinate at x equals 8. Find also the height of the mean ordinate of the curve between these points. Answer. Area equals 62.6 square units. Mean ordinate is 10.42. 15. Show that the radius of a circle, the area of which is twice the area of a polar diagram, is equal to the quadratic mean of all the values of r for that polar diagram. 16. Find the volume generated by the curve y equals plus or minus x over 6 times the square root of x open brackets 10 minus x close brackets, rotating about the axis of x. Answer. 436.3. This solid is pear-shaped. End of section 52. Section 53 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Calculus Made Easy by Silvanus P. Thompson. Chapter 20. Dodges, Pitfalls and Triumphs. Dodges. A great part of the labour of integrating things consists in licking them into some shape that can be integrated. The books, and by this is meant the serious books, on the integral calculus are full of plans and methods and dodges and artifices for this kind of work. The following are a few of them. Integration by parts. This name is given to a dodge, the formula for which is integral u dx equals ux minus integral x du add c. It is useful in some cases that you can't tackle directly, for it shows that if in any case integral x du can be found, then integral u dx can also be found. The formula can be deduced as follows. From page 37 we have d open brackets ux close brackets equals u dx add x du, which may be written u dx equals open brackets d ux close brackets minus x du, which by direct integration gives the above expression. Examples. 1. Find integral w sin w dw. Write u equals w, and for sin w dw write dx. We shall then have du equals dw, while integral sin w dw equals minus cos w equals x. Putting these into the formula, we get integral w sin w dw equals w open brackets minus cos w close brackets minus integral minus cos w dw equals minus w cos w add sin w add c. 2. Find integral x e to the power of x dx. Write u equals x, e to the power of x dx equals dv. Then du equals dx, v equals e to the power of x. And integral x e to the power of x dx equals x e to the power of x minus integral e to the power of x dx by the formula equals x e to the power of x minus e to the power of x equals e to the power of x open brackets x minus 1 close brackets add c. 3. Try integral cos squared theta d theta. U equals cos theta d theta equals dv. Hence du equals minus sin theta d theta, v equals sin theta. Integral cos squared theta d theta equals cos theta sin theta add integral sin squared theta d theta equals 2 cos theta sin theta all over 2 add integral open brackets 1 minus cos squared theta close brackets d theta equals sin 2 theta all over 2 add integral d theta minus integral cos squared theta d theta. Hence 2 integral cos squared theta d theta equals sin 2 theta all over 2 add theta, and integral cos squared theta d theta equals 2 sin theta all over 4 add theta over 2 add c. 4. Find integral x squared sin x dx. Write x squared equals u, sin x dx equals dv. Then du equals 2x dx, v equals minus cos x. Integral x squared sin x dx equals minus x squared cos x add to integral x cos x dx. Now find integral x cos x dx integrating by parts, as in example 1 above. Integral x cos x dx equals x sin x add cos x add c. Hence x squared sin x dx equals minus x squared cos x add 2x sin x add 2 cos x add c dash equals 2 open brackets x sin x add cos x open brackets 1 minus x squared over 2 close brackets add c dash. 5. Find integral square root of 1 minus x squared dx. Write u equals square root of 1 minus x squared dx equals dv. Then du equals minus x dx over square root of 1 minus x squared, and x equals v, so that integral square root of 1 minus x squared dx equals x square root 1 minus x squared add integral x squared dx over square root of 1 minus x squared. Here we may use a little dodge, for we can write integral the square root of 1 minus x squared dx equals integral open brackets 1 minus x squared close brackets dx all over the square root of 1 minus x squared equals dx over the square root of 1 minus x squared minus integral x squared dx over the square root of 1 minus x squared. Adding these two last equations, we get rid of integral x squared dx over the square root of 1 minus x squared, and we have 2 integral square root of 1 minus x squared dx equals x times the square root of 1 minus x squared, add integral dx over the square root of 1 minus x squared. Do you remember meeting dx over the square root of 1 minus x squared? It is got by differentiating y equals arc sin x. Hence its integral is arc sin x, and so integral square root of 1 minus x squared dx equals x square root of 1 minus x squared all over 2, add a half arc sin x, add c. You can try now some exercises by yourself. You will find some at the end of this chapter. Substitution. This is the same dodge as explained in chapter 9, page 66. Let us illustrate its application to integration by a few examples. 1. Integral square root of 3 add x dx. Let 3 add x equals u, dx equals du. Replace integral u to the power of a half du equals 2 over 3 u to the power of 3 over 2 equals 2 over 3 open brackets 3 add x close brackets to the power of 3 over 2. 2. Integral dx over e to the power of x add e to the power of minus x. Let e to the power of x equals u, du over dx equals e to the power of x, and dx equals du over e to the power of x. So that dx over e to the power of x add e to the power of minus x equals integral du over e to the power of x open brackets e to the power of x add e to the power of minus x close brackets equals integral du over u open brackets u add 1 over u close brackets equals integral du over u squared add 1. Du over u squared add 1 is the result of differentiating arc tan x. Hence the integral is arc tan e to the power of x. 3. Integral dx over x squared add 2x add 3 equals integral dx over x squared add 2x add 1 add 2 equals integral dx over open brackets x add 1 close brackets squared add open brackets square root of 2 close brackets squared. Let x add 1 equals u, dx equals du. Then the integral becomes integral du over u squared add open brackets square root of 2 close brackets squared. But du over u squared add a squared is the result of differentiating u equals 1 over a arc tan u over a. Hence one has finally 1 over the square root of 2 arc tan x add 1 all over the square root of 2 for the value of the given integral. Formulae of reduction are special forms applicable chiefly to binomial and trigonometrical expressions that have to be integrated and have to be reduced into some form of which the integral is known. Rationalisation and factorisation of denominator are dodges applicable in special cases, but they do not admit any short or general explanation. Much practice is needed to become familiar with these preparatory processes. The following example shows how the process of splitting into partial fractions, which we learned in chapter 13, page 118, can be made use of in integration. Take again integral dx over x squared add 2x add 3. If we split 1 over x squared add 2x add 3 into partial fractions, this becomes 1 over 2 square root of minus 2, open brackets, integral dx over x add 1 minus square root of minus 2 minus integral dx over x add 1 add the square root of minus 2 close brackets equals 1 over 2 square root of minus 2 log base e x add 1 minus square root of minus 2 over x add 1 add square root of minus 2. Notice that the same integral can be expressed sometimes in more than one way, which are equivalent to one another. Pitfalls. A beginner is liable to overlook certain points that a practised hand would avoid, such as the use of factors that are equivalent to either 0 or infinity, and the occurrence of indeterminate quantities such as 0/0. There is no golden rule that will meet every possible case. Nothing but practice and intelligent care will avail. An example of a pitfall which had to be circumvented arose in Chapter 18, page 189, when we came to the problem of integrating x⁻⁻1 dx. Triumphs. By triumphs must be understood the successes with which the calculus has been applied to the solution of problems otherwise intractable. Often in the consideration of physical relations one is able to build up an expression for the law governing the interaction of the parts or the forces that govern them, such expression being naturally in the form of a differential equation, that is, an equation containing differential coefficients with or without other algebraic quantities. And when such a differential equation has been found, one can get no further until it has been integrated. Generally it is much easier to state the appropriate differential equation than to solve it. The real trouble begins then only when one wants to integrate, unless indeed the equation is seen to possess some standard form of which the integral is known, and then the triumph is easy. The equation which results from integrating a differential equation is called its solution, and it is quite astonishing how in many cases the solution looks as if it had no relation to the differential equation of which it is the integrated form. Footnote: This means that the actual result of solving it is called its solution, but many mathematicians would say, with Professor Forsyth, every differential equation is considered as solved when the value of the dependent variable is expressed as a function of the independent variable by means either of known functions or of integrals, whether the integration in the latter can or cannot be expressed in terms of functions already known. End footnote. The solution often seems as different from the original expression as the butterfly does from the caterpillar that it was. Who would have supposed that such an innocent thing as dy/dx equals 1/a² - x² could blossom into y equals 1/2a log base e a add x over a minus x add c, yet the latter is the solution of the former. As a last example, let us work out the above together. By partial fractions, 1/a² - x² equals 1/2a open bracket a add x close bracket add 1/2a open bracket a minus x close bracket. dy equals dx over 2a open brackets a add x close bracket add dx over 2a open brackets a minus x close bracket. Y equals 1/2a open bracket integral dx over a add x add integral dx over a minus x close bracket equals 1/2a open brackets log base e open brackets a add x close bracket minus log base e open brackets a minus x close bracket equals 1/2a log base e a add x over a minus x add c. Not a very difficult metamorphosis. There are whole treatises, such as Boole's Differential Equations, devoted to the subject of thus finding the solutions for different original forms. End of section 53. Section 54 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Calculus Made Easy by Silvanus P. Thompson. Section 54. Exercises 19. 1. Find integral square root of a² - x² dx. Answer. X square root of a² - x² all over 2 add a² over 2 sin to the power of -1 x over a add c. 2. Find integral x log base e x dx. Answer. x² over 2 open brackets log base e x minus a half close brackets add c. 3. find integral x to the power of a log base e x dx. Answer. X to the power of a add 1 all over a add 1 open brackets log base ex minus 1 over a add 1 close brackets add c. 4. Find integral e to the power of x cos e to the power of x dx. Answer. Sin e to the power of x add c. 5. Find integral 1 over x cos open brackets log base ex close brackets dx. Answer. Sin open brackets log base ex close brackets add c. 6. Find integral x squared e to the power of x dx. Answer. E to the power of x open brackets x squared minus 2x add 2 close brackets add c. 7. Find integral open brackets log base ex close brackets to the power of a all over x dx. Answer. 1 over a add 1 open brackets log base ex close brackets to the power of a add 1 add c. 8. Find integral dx over x log base ex. Answer. Log base e open brackets log base ex close brackets add c. 9. Find integral 5x add 1 all over x squared add x minus 2 dx. Answer. 2 log base e open brackets x minus 1 close brackets add 3 log base c open brackets x add 2 close brackets add c. 10. Find integral open brackets x squared minus 3 close brackets dx all over x cubed minus 7x add 6. Answer. Half log base e open brackets x minus 1 close brackets add 1/5 log base e open brackets x minus 2 close brackets add 3/10 log base e open brackets x add 3 close brackets add c. 11. Find integral b dx all over x squared minus a squared. Answer. b over 2a log base e x minus a over x add a add c. 12. Find integral 4x dx all over x to the power of 4 minus 1. Answer. Log base e x squared minus 1 over x squared add 1 add c. 13. Find integral dx over 1 minus x to the power of 4. Answer. 1/4 log base e 1 add x over 1 minus x add a half arc tan x add c. 14. Find integral dx over x times the square root of a minus bx squared. Answer. 1 over root a log base e root a minus bx squared all over x root a. Let 1 over x equals v, then in the result let the square root of v squared minus b over a equal v minus u. You had better differentiate now the answer and work back to the given expression as a check. End of section 54. Section 55 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Calculus Made Easy by Silvanus P. Thompson. Chapter 21. Finding some Solutions, Part 1. In this chapter, we go to work finding solutions to some important differential equations, using for this purpose the processes shown in the preceding chapters. The beginner, who now knows how easy most of these processes are in themselves, will here begin to realise that integration is an art. As in all arts, so in this, facility can be acquired only by diligent and regular practice. He who would attain that facility must work out examples and yet more examples, such as are found abundantly in all the regular treatises on the calculus. Our purpose here must be to afford the briefest introduction to serious work. Example 1. Find the solution of the differential equation ay add b dy over dx equals 0. Transposing, we have b dy over dx equals minus ay. Now the mere inspection of this relation tells us that we have got to do with a case in which dy over dx is proportional to y. If we think of the curve which will represent y as a function of x, it will be such that its slope at any point will be proportional to the ordinate at that point, and will be a negative slope if y is positive. So obviously the curve will be a die-away curve, and the solution will contain e to the power of minus x as a factor. But, without presuming on this bit of sagacity, let us go to work. As both y and dy occur in the equation and on opposite sides, we can do nothing until we get both y and dy to one side, and dx to the other. To do this, we must split our usually inseparable companions dy and dx from one another. dy over y equals minus a over b dx. Having done the deed, we now see that both sides have got into a shape that is integratable, because we recognise dy over y, or 1 over y times dy, as a differential that we have met with when differentiating logarithms, so we may at once write down the instructions to integrate. Integral dy over y equals integral minus a over b dx, and doing the two integrations we have log base ey equals minus a over bx add log base ec, where log base ec is the yet undetermined constant of integration. Footnote. We may write down any form of constant as the constant of integration, and the form log base ec is adopted here by preference, because the other terms in this line of equation are, or are treated as logarithms, and it saves complications afterward if the added constant be of the same kind. End footnote. Then, delogarising, we get y equals c e to the power of minus a over b x, which is the solution required. Now this solution looks quite unlike the original differential equation from which it was constructed, yet to an expert mathematician they both convey the same information as to the way in which y depends on x. Now, as to the c, its meaning depends on the initial value of y. For if we put x equals 0 in order to see what value y then has, we find that this makes y equals c e to the power of minus 0, and as e to the power of minus 0 equals 1, we see that c is nothing else than the particular value of y at starting. Footnote. Compare what was said about the constant of integration with reference to figure 48 on page 184 and figure 51 on page 187. End footnote. This we may call y0, and so write the solution as y equals y0 e to the power of minus a over b x. Example 2. Let us take as an example to solve ay add b dy over dx equals g, where g is a constant. Again, inspecting the equation will suggest 1. That somehow or other e to the power of x will come into the solution, and 2. That if at any point of the curve y becomes either a maximum or a minimum, so that dy over dx equals 0, then y will have the value of g over a. But let us go to work as before, separating the differentials and trying to transform the thing into some integrable shape. b dy over dx equals g minus ay. dy over dx equals a over b, open brackets, g over a minus y, close brackets. dy all over y minus g over a equals minus a over b dx. Now we have done our best to get nothing but y and dy on one side and nothing but dx on the other, but is the result on the left side integrable? It is of the same form as the result on page 145, So writing the instructions to integrate, we have integral dy all over y minus g over a equals minus integral a over b dx. And doing the integration and adding the appropriate constant, log base e, open brackets, y minus g over a, close brackets, equals minus a over bx add log base e c, whence y minus g over a equals c e to the power of minus a over b x, and finally y equals g over a add c e to the power of minus a over b x, which is the solution. If the condition is laid down that y equals 0 when x equals 0, we can find c, for then the exponential becomes equals 1, and we have 0 equals g over a add c, c equals minus g over a. Putting in this value, the solution becomes y equals g over a, open brackets, 1 minus e to the power of minus a over b x, close brackets. But further, if f grows indefinitely, y will grow to a maximum, for when x equals infinity, the exponential equals 0, giving y max equals g over a. Substituting this, we get finally y equals y max, open brackets, 1 minus e to the power of minus a over bx, close brackets. This result is also of importance in physical science. Example 3. Let ay add b dy over dt equals g times sin 2 pi nt. We shall find this much less tractable than the preceding. First divide through by b. dy over dt add a over by equals g over b times sin 2 pi nt. Now as it stands, the left side is not integratable, but it can be made so by the artifice, and this is where skill and practice suggest a plan, of multiplying all the terms by e to the power of a over bt, giving us dy over dt e to the power of a over bt, add a over by e to the power of a over bt equals g over b e to the power of a over bt times sin 2 pi nt, which is the same as dy over dt e to the power of a over bt add y d open brackets e to the power of a over bt close brackets over dt equals g over b e to the power of a over bt times sin 2 pi nt. And this being a perfect differential may be integrated thus, since if u equals y e to the power of a over bt, du over dt equals dy over dt e to the power of a over bt add y d open brackets e to the power of a over bt close brackets over dt. Y equals e to the power of a over bt equals g over b integral e to the power of a over bt times sin 2 pi nt dt add c, or y equals g over b e to the power of minus a over bt integral e to the power of a over bt times sin 2 pi nt dt add c e to the power of minus a over bt. Equation A. The last term is obviously a term which will die out as t increases, and may be omitted. The trouble now comes in to find the integral that appears as a factor. To tackle this we resort to the device of integration by parts, the general formula for which is integral u dv equals uv minus integral v du. For this purpose we write u equals e to the power of a over bt and dv equals sin 2 pi nt dt. We shall then have du equals e to the power of a over bt times a over b dt, and b equals minus 1 over 2 pi n cos 2 pi nt. Inserting these, the integral in question becomes integral e to the power of a over bt sin 2 pi nt dt equals minus 1 over 2 pi n times e to the power of a over bt times cos 2 pi nt minus integral minus 1 over 2 pi n cos 2 pi nt times e to the power of a over bt times a over b dt equals minus 1 over 2 pi n times e to the a over bt cos 2 pi nt add a over 2 pi nb integral e to the power of a over b t times cos 2 pi nt dt. Equation b. The last integral is still irreducible. To evade the difficulty, repeat the integration by parts of the left side, but treating it in the reverse way by writing u equals sin 2 pi nt and dv equals e to the power of a over bt dt, whence du equals 2 pi n times cos 2 pi nt times dt, and v equals b over a e to the power of a over bt. Inserting these, we get integral e to the power of a over bt times sin 2 pi nt dt equals b over a times e to the power of a over bt times sin 2 pi nt minus 2 pi nb all over a integral e to the power of a over bt times cos 2 pi nt dt. Equation c. Noting that the final intractable integral in c is the same as that in b, we may eliminate it by multiplying b by 2 pi nb all over a and multiplying c by a over 2 pi nb and adding them. The result, when cleared down, is integral e to the power of a over bt times sin 2 pi nt dt equals e to the power of a over bt open brackets ab sin 2 pi nt minus 2 pi nb squared cos 2 pi nt all over a squared add 4 pi squared n squared b squared close brackets. Inserting this value in a, we get y equals g open brackets a sin 2 pi nt minus 2 pi nb cos 2 pi nt all over a squared add 4 pi squared n squared b squared close brackets. To simplify still further, let us imagine an angle phi such that tan phi equals 2 pi nb over a. Then sin phi equals 2 pi nb all over the square root of a squared add 4 pi squared n squared b squared, and cos phi equals a over the square root of a squared add 4 pi squared n squared b squared. Substituting these, we get y equals g cos phi sin 2 pi nt minus sin phi cos 2 pi nt all over the square root of a squared add 4 pi squared n squared b squared, which may be written y equals g sin open brackets 2 pi nt minus phi close brackets all over the square root of a squared add 4 pi squared n squared b squared, which is the solution desired. This is indeed none other than the equation of an alternating electric current, where g represents the amplitude of the electromotive force, n the frequency, a the resistance, b the coefficient of self-induction of the circuit, and phi is an angle of lag. End of section 55. Section 56 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Calculus Made Easy by Silvanus P. Thompson. Chapter 21, Finding Some Solutions, Part 2. Example 4. Suppose that m dx add n dy equals 0. We could integrate this expression directly if m were a function of x only and n a function of y only, but If both m and n are functions that depend on both x and y, how are we to integrate it? Is it itself an exact differential? That is, have m and n each been formed by partial differentiation from some common function u or not? If they have, then delta u over delta x equals m and delta u over delta y equals n. And if such a common function exists, then delta u over delta x dx add delta u over delta y dy is an exact differential. Now the test of the matter is this. If the expression is an exact differential, it must be true that dm over dy equals dn over dx, for then d open brackets du close brackets all over dx dy equals d open brackets du close brackets over dy dx, which is necessarily true. Take as an illustration the equation open brackets 1 add 3xy close brackets dx add x squared dy equals 0. Is this an exact differential or not? Apply the test. D open brackets 1 add 3xy close brackets over dy equals 3x, and d open brackets x squared close brackets over dx equals 2x, which do not agree. Therefore it is not an exact differential, and the two functions 1 add 3xy and x squared have not come from a common original function. Is it possible in such cases to discover, however, an integrating factor, that is to say, a factor such that if both are multiplied by this factor, the expression will become an exact differential? There is no one rule for discovering such an integrating factor, but experience will usually suggest one. In the present instance 2x will act as such. Multiplying by 2x we get open brackets 2x add 6x squared y close brackets dx add 2x cubed dy equals 0. Now apply the test to this. D open brackets 2x add 6x squared y close brackets over dy equals 6x squared. D open brackets 2x cubed close brackets over dx equals 6x squared, which agrees. Hence this is an exact differential and may be integrated. Now, if w equals 2x cubed y, dw equals 6x squared y dx add 2x cubed dy, hence integral 6x squared y dx add integral 2x cubed dy equals w equals 2x cubed y, so that we get u equals x squared add 2x cubed y add c. Example 5. Let d2y over dt squared add n squared y equals 0. In this case we have a differential equation of the second degree in which y appears in the form of a second differential coefficient as well as in person. Transposing, we have d2y over dt squared equals minus n squared y. It appears from this that we have to do with a function such that its second differential coefficient is proportional to itself, but with reversed sign. In chapter 15 we found that there was such a function, namely the sine, or the cosine also, which possessed this property. So, without further ado, we may infer that the solution will be of the form y equals a sin open brackets pt add q close brackets. However, let us go to work. Multiply both sides of the original equation by 2 dy over dt and integrate, giving us 2 d2y over dt squared dy over dt add 2x squared y dy over dt equals 0, and us 2 d2y over dt squared dy over dt equals d open brackets dy over dt close brackets squared over dt open brackets dy over dt close brackets squared add n squared open brackets y squared minus c squared close brackets equals 0, c being a constant. Then, taking the square roots, dy over dt equals minus n square root of y squared minus c squared, and dy over square root of c squared minus y squared equals n dt. But it can be shown that 1 over the square root of c squared minus y squared equals d open brackets, arc sin y over c, close brackets, over dy, whence, passing from angles to sines, arc sin y over c equals nt add c1, and y equals c sin open brackets nt add c1, close brackets, where c1 is a constant angle that comes in by integration, or preferably this may be written y equals a sin nt add b cos nt, which is the solution. Example 6. d2y over dt squared minus n squared y equals 0. Here we obviously have to deal with a function y which is such that its second differential coefficient is proportional to itself. The only function we know that has this property is the exponential function, and we may be certain therefore that the solution of the equation will be of that form. Proceeding as before, by multiplying through by 2 dy over dx, and integrating, we get 2 d2y over dx squared dy over dx minus 2x squared y dy over dx equals 0, and as 2 d2y over dx squared dy over dx equals d open brackets dy over dx close brackets squared over dx open brackets dy over dx close brackets squared minus n squared open brackets y squared add c squared close brackets equals 0, dy over dx minus n square root of y squared add c squared equals 0, where c is a constant, and dy over the square root of y squared add c squared equals n dx. Now, if w equals log base e open brackets y add the square root of y squared add c squared close brackets equals log base e u, dw over du equals 1 over u. du over dy equals 1 add y over the square root of y squared add c squared equals y add square root of y squared add c squared all over the square root of y squared add c squared, and dw over dy equals 1 over the square root of y squared add c squared. Hence, integrating, this gives us log base e open brackets y add square root of y squared add c squared close brackets equals nx add log base e big C. Y add square root of y squared add c squared equals big C e to the power of nx, equation 1. Now, open brackets, y add square root of y squared add c squared close brackets times open brackets minus y add square root of y squared add c squared close brackets equals c squared. Whence, minus y add square root of y squared add c squared equals c squared over big C e to the power of minus nx, equation 2. Subtracting equation 2 from equation 1 and dividing by 2, we then have y equals half big C e to the power of nx minus a half c squared over big C e to the power of minus nx, which is more conveniently written y equals a e to the power of nx add b e to the power of minus nx, or the solution, which at first sight does not look as if it had anything to do with the original equation, shows that y consists of two terms, one of which grows logarithmically as x increases, and of a second term which dies away as x increases. Example 7. Let b d2y over dt squared add a dy over dt add gy equals 0. Examination of this expression will show that, if b equals 0, it has the form of example 1, the solution of which was a negative exponential. On the other hand, if a equals 0, its form becomes the same as that of example 6, the solution of which is the sum of a positive and a negative exponential. It is therefore not very surprising to find that the solution of the present example is y equals open brackets e to the power of minus mt close brackets open brackets a e to the power of nt add b e to the power of minus nt close brackets, where m equals a over 2b and n equals the square root of a squared over 4b squared minus g over b. The steps by which this solution is reached are not given here. They may be found in advanced treatises. Example 8. d2y over dt squared equals a squared d2y over dx squared. It was seen that this equation was derived from the original y equals big F as a function of x add at, add little f as a function of x minus at, where big F and little f were any arbitrary functions of t. Another way of dealing with it is to transform it by a change of variables into d2y over du dv equals 0, where u equals x add at and v equals x minus at, leading to the same general solution. If we consider a case in which big F vanishes, then we have simply y equals little f as a function of x minus at, and this merely states that at the time t equals 0, y is a particular function of x and may be looked upon as denoting that the curve of the relation of y to x has a particular shape. Then any change in the value of t is equivalent simply to an alteration in the origin from which x is reckoned. That is to say, it indicates that, the form of the function being conserved, it is propagated along the x direction with a uniform velocity a, so that whatever the value of the ordinate y at any particular time t0, at any particular point x0, the same value of y will appear at the subsequent time t1 at a point further along, the abscissa of which is x0 add a open brackets t1 minus t0 close brackets. In this case, the simplified equation represents the propagation of a wave, of any form, at a uniform speed along the x direction. If the differential equation had been written d2y over dt squared equals k d2y over dx squared, the solution would have been the same, but with the velocity of propagation would have the value a equals the square root of k over m. You have now been personally conducted over the frontiers into the enchanted land, and in order that you may have a handy reference to the principal results, the author, in bidding you farewell, begs to present you with a passport in the shape of a convenient collection of standard forms. In the middle column are set down a number of the functions which most commonly occur. The results of differentiating them are set down on the left, the results of integrating them are set down on the right. May you find them useful. End of section 56.
Section 57 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Rachel. Calculus Made Easy by Silvanus P. Thompson. Epilogue and Apologue. It may be confidently assumed that when this tractate, Calculus Made Easy, falls into the hands of the professional mathematicians, they will, if not too lazy, rise up as one man and damn it as being a thoroughly bad book. Of that there can be, from their point of view, no possible manner of doubt whatever. It commits several most grievous and deplorable errors. First, it shows how ridiculously easy most of the operations of the calculus really are. Secondly, it gives away so many trade secrets. By showing you that, what one fool can do, other fools can do also, it lets you see that these mathematical swells, who pride themselves on having mastered such an awfully difficult subject as the calculus, have no such great reason to be puffed up. They like you to think how terribly difficult it is, and don't want that superstition to be rudely dissipated. Thirdly, among the dreadful things they will say about "so easy," is this, that there is an utter failure on the part of the author to demonstrate with rigid and satisfactory completeness the validity of sundry methods which he has presented in simple fashion, and has even dared to use in solving problems. But why should he not? You don't forbid the use of a watch to every person who does not know how to make one. You don't object to the musician playing on a violin that he has not himself constructed. You don't teach the rules of syntax to children until they have already become fluent in the use of speech. It would be equally absurd to require general rigid demonstrations to be expounded to beginners in the calculus. One other thing will the professed mathematicians say about this thoroughly bad and vicious book, that the reason why it is so easy is because the author has left out all the things that are really difficult. And the ghastly fact about this accusation is that it is true. That is indeed why the book has been written for the legion of innocents who have hitherto been deterred from acquiring the elements of the calculus by the stupid way in which its teaching is almost always presented. Any subject can be made repulsive by presenting it bristling with difficulties. The aim of this book is to enable beginners to learn its language, to acquire familiarity with its endearing simplicities, and to grasp its powerful methods of solving problems, without being compelled to toil through the intricate, out of the way, and mostly irrelevant, mathematical gymnastics so dear to the unpractical mathematician. There are amongst young engineers a number on whose ears the adage that "what one fool can do, another can," may fall with a familiar sound. They are earnestly requested not to give the author away, nor to tell the mathematicians what a fool he really is. End of Section 57. End of Calculus Made Easy, by Silvanus P. Thompson.